All right. It says that we are live. Hello and welcome. Tonight we have Space Audits versus Astronomy Live in a flat Earth versus globe debate. The subject for tonight's debate is the celestial theodolite. Does it sufficiently support the flat Earth, or does it leave a lot to be desired? This debate will have the following structure. We will start with a 15-minute opening so that each of you can make your case. This will be followed by a 20-minute rebuttal. After that, we will go into an open discussion that can go for as long as it needs to. We will then take questions from the audience via super chats, and then we will finish with a final statement from both of you. At this point, Alan, I would like to give you one of two options. Since my audience has never heard of the celestial theodolite and I only have a vague understanding of it, I believe it would be beneficial to have you go first in this debate so that you can take the opportunity to explain what it is and what you assert it shows. That way, everyone can establish a solid baseline on the subject, and from somebody who actively promotes it, that being you. So if you choose that option, I would be more than happy to give you extra time during your opening. Additionally, I would also be willing to grant you the last word before we end the debate. Option 2 is a coin flip, and we let fate take over with that one. So of the two options, Alan, which one would you like to do?
No, for audience coherence, you're absolutely right. That's very generous. And obviously, Astronomy Live agreed to that beforehand. Very much appreciated. That's very generous of you. I accept.
Excellent. So, Alan, for your intro, I'm going to grant you 2 extra minutes, and we will go from there. So with that, Alan, go ahead and get ready. Let me set up the timer on my end so that we can get ready. Here we go. Do. All right. And it is on. All right. So with that, your time will start as soon as I see your screen share, because I assume you're going to be sharing something with us. There we go. Okay, and your time starts in 3, 2, 1, go.
All right. So, like Red said, let me begin with an overview of the celestial theodolite itself. So it is a method of measuring the precise timing of a celestial occlusion, which the moment when the celestial object intersects with a terrestrial feature, which we use as our reference point. So in this case, it'll be a mountain peak. By recording when and where the intersection occurs, we can compare the observed timing against the prediction made by two competing horizontal reference lines. Whether the Earth is a plane or a sphere, the geometric aligning of the occlusion time can distinguish between those. When using the celestial sphere model to establish a terrestrial sphere, it becomes an internally consistent model. Because the model is self-referential, it cannot be contradicted by observation alone. The celestial theodolite provides a novel method of determining whether the conceptual model actually corresponds to physical reality. By measuring the precise timing of the celestial occlusion against the terrestrial reference points, we can externally test this internally consistent model. Because the geometry of a plane and a sphere is well established and proven by basic theorems, we can do a geometric analysis on the position of the stars relative to the peak and compare mutually exclusive predictions. So that's the broad overview. Here's a little more technical. The celestial theodolite is a method of recording the star timing of an occlusion with a terrestrial feature, such as a mountain peak. Using the mountain peak as our crosshair and the occlusion timing, we can make geometric intersection comparisons of the geocentric position of the star to test the shape of the Earth using the null hypothesis methodology. As a control variable, the known mountain elevation with respect to sea level will be used to calculate the delta peak elevation with respect to the observer's elevation above sea level as well. The independent variable will be the observer's distance and relative elevation to the peak. So that's going to dictate the angle difference between them, which is going to be our dependent variable. The combination of distance and elevation allows us to calculate mutually exclusive predictions for geometric alignments and the corresponding time of an occlusion, which gives us the dependent variable, or the time of occlusion, or the angle in celestial navigation. And in the two-sphere model, time and angle are synonymous. Because the celestial sphere and terrestrial sphere use a fictitious observer to calculate the geocentric position of the star at a linearized rate of 60 nautical miles per degree following sidereal time, the geocentric position and angle to any star can be calculated for an observer anywhere on Earth so long as they know the time. So the purpose of this debate, I was talking about the lack of geometric intersection comparisons on the globe side. I run a weekly show called Celestial Theodolite Update, and every week we go over the geometric implications of the celestial theodolite, and there's not a lot of engagement on that end. And what the globe lads would like to do is analyze the apparent. So we're going to include that into geometric analysis for this as well and show how it doesn't help. So it was stated that our premise was fundamentally flawed in this and how we're using stellar occlusions to determine the geometry of Earth. And so we're going to go through some definitions here and clarifications for everything. And I think that we're actually going to agree on a lot of points in regarding celestial navigation and how to predict occlusions. Okay, so this is going to be a really, it can get kind of dense in here. There's a lot of data to go over, a lot of points. Everything can be found here on the Celestial Theodolite. Let me get this link to Reds real quick in the private chat. Can you put this in the YouTube for everyone, please? So in case they want the sources. So if you want any sources or to check back on anything later, you can have the link here. The link to all my Obsidian stuff and the spreadsheet is here. So definitions. You can find it all here and then just click on the stuff and go over it. So definitions. So Besselian elements, this is something where they use to calculate occlusions and eclipses, and this is based on the geometric intersections here. So this is a fundamental plane coordinate system here where they have the observer at the center of the Earth, the fictitious observer, making the calculations all relative to that for the intersection points. So this is well and established here. Conjunctions, this is also usually tabulated with the geocentric position here. I'm not aware of any apparent ephemerises or whatever. They all seem to be using the geocentric position for how they calculate things. Now, keep in mind, I'm not saying that refraction, doesn't possibly exist or what have you. But what I am saying is that for the baseline of comparison, you need to start with the geocentric position to have that reference point for it to be relative to. So here's eclipse predictions from NASA here. This is from Fred Aspernek, who gathered a bunch of eclipse data from different countries, and everything that he tabulated and put into form to predict out eclipses is all done through the geocentric position, and they don't consider refraction in the analysis there. Celestial navigation from Umland in 2015, talking about the celestial navigation it always refers to the geocentric altitude of a body. The altitude was measured by a fictitious observer on the plane of the celestial horizon at the center of Earth, which coincides to the celestial sphere. So this is how they link the celestial sphere, which is a sphere of infinite radius, to the terrestrial sphere, so-called, which is a sphere of radius 3959. And in doing that, they linearize the 60 nautical mile per degree for the stars with respect to sidereal time. And that is how they get the reference point for where the star should be versus where it is optically. And then every 10 degrees in elevation of refraction, there's a specific amount of refraction that you remove. So you do a site reduction, and that's how you obtain the geocentric position. When you get closer to the horizon, you'll see that the equations start to increase at like a hyperbolic rate, and to compensate for the deviation from the star, where it should have already been occluded by the curvature of Earth. It's still visible. It's not following that rate. So the angular difference, they say, is astronomical refraction. So again, just defining that geocentric position for everything. So the geocentric position, meaning the center of the Earth is taken as the origin. It is the viewpoint where the Earth stands still, and the sphere rotates around it daily. Like I said, just establishing that linearized rate, making it all relative to that. So geometric, when we talk about geometric positions, we're talking about the true position, whether it be the true position of a star or it be the unrefracted position of a mountain peak, so the geometric angle to the mountain peak. Now, in terms of using occlusions with respect to terrestrial features, there's actually a history of this that I stumbled upon from a manual of spherical and practical astronomy from William Chavant, who was cited in the supplement to the nautical ephemeris and American Almanac, where they talk about refraction and how to compensate for that, because that book itself is all about geometric intersections and using that for navigation as well, and how they tie that to positions on Earth. So again, anyway, here we have an example of the French, who were using occlusions with terrestrial features at zenith distances anywhere from 80 degrees to 20 degrees off the horizon. So what they would do is they would time and occlusion, they would write the time down. They would have their local solar time. They would time the occlusion, and then another occlusion would occur. So they would have to wait for two of them, and they would take that time difference between them and calculate what the sidereal variance is from that stellar event. And they make a note here that if you're at a zenith distance of, if you're at 20 degrees at the horizon, so if your zenith distance is 80, then you have to remove refraction. If you're above that, then you can just basically consider the apparent position as good enough as the true position, because the deviation isn't very big. So yeah, they're removing the refraction. They're calculating for the refraction to calculate where the geocentric position of the star is at the time of an occlusion to help determine sidereal time. So there's an interesting use case of what we're doing. So the null hypothesis, real quick. How am I doing on time, Red?
Currently, you're at 8 minutes 35.
Okay, thank you. I'll speed it up. Okay, so the null hypothesis here is our H0 is that the Earth is a globe. The H1 is that the Earth is not a globe. I went over the independent variables earlier. That's the observer elevation and the mountain peak. And the control is the elevation of the mountain peak, because it's the known fixed quantity that doesn't change. The dependent variable is the angle. So when we do a geometric analysis at the time of occlusion, we should be able to establish that the globe makes the correct prediction based on its deviation from a plane, which is the drop over distance to the mountain peak. So math stuff. We're going to get into, oh no, why is the picture not loaded? Give me 1 second. This is pivotal to the...
I have stopped your time.
Thank you, sir. So sorry.
So we are paused at 9 minutes and 28 seconds. Let me know when you're ready to pick it back up.
Yes, sir. Let's see. Maybe it'll just reload and magically work. Inshallah. Yep, there we go. Okay.
All right. I'm starting your time back up. It's working?
Yep.
Okay. I'm starting your time back up in 3, 2, 1, go.
All right, cool. So there's a couple of things needed to understand the basic analysis of the celestial theodolite, and that is the 1 second here. Get back. Okay. So starting with central angle theorem, that is when two radii intersect the circumference of a circle or a sphere, that creates an angle or an arc across the surface of it. So the arc between D and E here is this represented by this angle here. So in the case of Earth, you would have Earth's radius. These lines would be to the surface. The angle between them would represent distance on the surface, or in meters, or by an angular amount. So you can convert the two by this equation here, which is distance over radius, which gives you the angle in radians, and you can convert that to degrees. But anyway, that's how you get the angular. That's called a central angle. Next part is the inscribed angle theorem. The inscribed angle theorem is that half of the central angle is going to be is the inscribed angle, essentially, and what that represents in terms of the globe is the drop over distance of the arc length. So the elevation difference from a tangent on a plane between D and E on a globe here is represented angularly by half of the central angle. So if I messed up on the thing here, but this is supposed to be showing 25 for the pink here. Actually, I have it right here. Let me swap that out. All right. Sorry, that's going to bug me. Okay, so it's showing the half gamma here. That is the half central angle, and that's how that relates to drop over distance of the arc length. So if you know the arc length, you can know what the drop over distance is and calculate that by converting it into meters using a tangent function, or you can use a Sagitta approximation factored by 4, and that'll give you the same result. But in any case, there's one more component to know, and that's chord tangent theorem. And this states that the angle difference between a chord and a tangent on a sphere here is going to be half of the central angle as well. It's going to be equal to that. So in this case here, we see that the central angle drop over distance creates a deviation from a plane by 15 degrees, and that happens to be the half central angle in every case. And like I said, you can convert that into meters to find out what that is. So when we go over data points, we'll be using Pike's Peak as an example. So the arc length is going to be 27 arc minutes, which is a distance of 50 0.5 kilometers, and that's going to give a drop over distance of 13 arc minutes, which comes out to be 200 feet. So that's how all that relates in terms of the numbers that we'll look at. So basically, what this means is that if you're on a globe, your midpoint of the horizon is cut off by this Earth curvature between you and this drop over distance here. So that's how all that relates. Now, what we can do is take occlusions and then add the arc length back and check where the positions of the stars are at. So the way that the globe breaks down occlusion predictions would be basically the star only has to drop half of the distance or half of the arc length because it's already lowered by the amount of Earth curvature, because the celestial sphere and terrestrial sphere are 1-to-1. And that's why they get the earlier alignment for their prediction, where the flat Earth has a longer prediction because we traverse the entire arc length, because there's not going to be an intersection relative to that initial point. Because that's the difference between a plane and a sphere, geometrically, and proved by Euclid's theorems and postulates there. So earlier, like I mentioned, we use arctan rise over run for the flat Earth prediction. That gives us the angle to the peak, and for the and that also gives us we can also get the central angle off of that. Now, as per chord tangent theorem, we can subtract the 13 arc minutes of drop over distance from the flat Earth prediction that comes out of this for Pikes Peak, and that comes out to be 2 degrees and 17 arc minutes. So that's what the globe predicts geometrically in terms of what their geometric angle to the peak is on a globe. That's the deviation from the plane. Now we have the central geometric position of the star here is equal to the calculated angle to the peak using rise over run. That's our condition for occlusion. And then same for the globe as well. Their condition would be flat Earth angle minus the drop over distance when the star intersects with that 217 angle relative to the observer. That would be when they predict their occlusion. So here's the math difference for that. So one using spherical trig, pure spherical trig, we arrive at 217.38 in arc seconds, and then using rise over run minus half the central angle, we get 217.42. So a small arc second difference for the purposes of this. They're identical. Okay, now this brings us to the data sheet on the spreadsheet. So we have a variety of mountains and distances here and stars that we can go over. But what this all represents primarily is this. How am I doing on time, Red?
Currently at 14:48.
Okay, cool. I got till 16, right?
17.
17. Okay. So for the geometric analysis here, we have there's a systemic error that's present in all the measurements here, and it's that the globe misses their intersection angle by what they predict as drop over distance. And if you take the intersection differences from both our positions, from the rise over run to the peak and from the angle predicted at the observer, if you add those together, they end up canceling out. So it shows that the initial artifact of the rise over run condition set by the globe is the systemic error. If we go down here and look at what it would look like if the globe had the occlusions that correspond to that geometry, when you add the error to it, it would add to our error, and we would be off by the essentially the entire arc length, but specifically the rise over run to the arc. The drop over distance to the arc length. So because it's an elevation difference on a sphere, we would be off by that whole amount, but it actually cancels out in every measurement exactly. So another part of this is when we
1 minute remaining.
Thank you, sir. Now we're criticized for, you don't calculate for refraction. You don't account for refraction. Well, adding refraction exactly compensates for the drop over distance in every measurement, or it exceeds the amount of drop over distance by a factor of either 1.5 or times 6 in some cases. So in every scenario, when you go through these, you'll find that when they're always over, except for this case where the distance was extremely far. The refraction wasn't enough to compensate for the lift of it. But yeah, other than that, every single time it more than compensates for the drop over distance. So in other words, it's adding back what it took out as a correction for drop over distance. And then this also extends to the correction is so extreme that in some cases it even covers the entire central angle, and otherwise it's flattening out and recovering the flat Earth angle. When per these theorems and postulates from Euclid, especially this tangent chord theorem, at the time of
That's
occlusion,
time. Go ahead and finish the thought.
Thank you. At the time of occlusion, when we add the arc length back, we should be off in elevation difference by the half gamma that we didn't account for. That drop over distance should be present in our overshooting of the elevation, but it's the opposite. The globe always overshoots. Thank you.
Thank you so much. And I also shared the link that you gave me to the live chat. And at the end of this, I will go ahead and include it in the description. So, Astronomy Live, it is now your turn. You will have 15 minutes, and your time will start the very moment I hear you start. So, let me go ahead and add your screen share here. All right, ready when you are.
All right, can you hear me okay?
Yes.
Okay, great. So, hi all, I'm Astronomy Live, if you haven't seen me before. Tonight we're going to be talking about the globe versus the celestial theodolite and which model better comports with reality. So, Alan just described for you the celestial theodolite. I'm going to try to break down some basics for you to help everyone understand. The celestial theodolite method involves timing the occultation of a star as it goes behind a distant mountaintop in order to infer the angle to the top of that mountain based on stellarium's prediction for the elevation of that star. Alan's claim is that the star will be occluded by a distant object like a mountaintop when the geometric angle to the star, shown in orange in this diagram, lines up with the geometric angle to the mountain from the perspective of the observer. Because Earth is flat in this model, the claim is also that the angle to the star will be the same as seen from the mountaintop as it would be for the observer position. To find what the angle should be, celestial theodolite proponents set the observer position to the mountaintop in programs like Stellarium, not the actual observer position. They also turn refraction off to get the predicted angle of the star, believing that the occlusion will occur when the geometric angle of the star equals the geometric angle of the peak, again shown by the orange line. Because this is a flat Earth model, the results of the occlusion timing are compared to the rise over the run angle based on the height and distance of the mountain without any amount of it hidden by curvature. The globe predicts that for a distant object or mountain, there will of course be some amount of drop in the angle to the peak due to the curvature of the Earth. Our model also says that refraction still matters and that the star will be occluded at the moment the apparent position of the peak lines up with the apparent position of the star. And that's shown by the bending red line here due to refraction. Because the peak's position is refracted less than the star, the geometric angle of the star, by this orange line, is lower than the geometric angle to the peak, shown by the upper orange line. Because the refracted light arrives at the observer from a steeper angle, we perceive it as a higher apparent angle than the geometric angle. The green line represents a straight line projected at that apparent angle, and it forms a tangent with the refracted red line at the point that it reaches the observer. Using an aquarium filled with water and a copious amount of pool salt, I created a concentration and density gradient to demonstrate the effect that it has on refraction of light passing through the gradient. As you can see in this picture, a laser will curve down towards the higher density once the salt settles enough to establish a gradient. An observer standing at the spot where the laser is hitting the bottom of the tank on the right would perceive the laser as coming from a steeper angle of elevation than the geometric angle to the laser. Here you can see the laser passing by a SpongeBob figurine just passing by his arm. If SpongeBob were to fully block the light, a person standing where the light is striking the bottom of the tank would perceive the light as having been occluded at the higher refracted apparent elevation they last saw the light coming from. Here are 3 simulated stars on the opposite side of the aquarium from an underwater camera. You can see a metal plate the stars are attached to, and note the 2 black thumb screws. The lower thumb screw is vertically compressed by the higher amount of refraction lower in the tank, similar to the higher refraction we see at lower elevations over the horizon on Earth. The lowest of these 3 simulated stars in this picture is actually geometrically below the oval SpongeBob base in the picture. Stars are not occluded until their higher refracted apparent positions coincide with the apparent position of the object that is occluding them. This is the crux of a fundamental flaw in the celestial theodolite concept. In December, Alan challenged me to measure occultation timings. Since there are no mountains in Florida, I decided to use a different type of object that can be found at even higher altitudes and observed at great distances: airplanes. I decided to use Rocket Tracker to film airplanes at or near cruising altitude while simultaneously receiving ADS-B data transmitted by the plane using an antenna and an RTL SDR. I was able to capture multiple stars occluded by planes over a few nights, and I will be invoicing Alan for my successful celestial theodolite observations. The ADS-B data transmitted by each airplane contains its latitude, longitude, and altitude to within an uncertainty of about 45 meters vertically and less than that laterally. That altitude is the barometric altitude. All of the planes I tracked were above the transition altitude, meaning they're all set to the same standard altimeter setting. I converted this altitude back to GPS altitude using weather balloon data from each night that I performed an observation. This right here is the ADS-B data for the first airplane I observed occulting a star, a Spirit Airlines jet which flew in front of the star Talitha Australis on January 5th Eastern Time. Note the time listed in the updated column here is based on the oscillator in the RTL SDR receiver, and it's less accurate than the computer clock time shown at the bottom right corner of the screenshot. For my measurements, I always used the computer clock time synced in the field by a GPS receiver. Here's the occultation of Talitha Australis by Spirit Airlines. All of these videos will be available for direct download as a link in the video description so that you can review them without the additional streaming compression. You can see Talitha Australis there, and it's occluded by the plane. If you blinked and missed it, here's a frame showing the occultation of the star, completely blocked by the plane. Here's Allegiant 453 occluding star HIP 47693. It's right there. And once again, here's a frame of the occultation itself. The star's identity was confirmed by plate solving. Here's the ADS-B data from the Allegiant 453 occlusion. Here's Business Jet with a call sign Jet Speed 691, occulting star HIP 23078. The timestamp shown up here at the top left of these videos is universal time, by the way. And here's a still frame from the Jet Speed 691 occultation. Here's the ADS-B data for Jet Speed 691. Here's American Airlines 1517 occulting star HIP 39850. And here's a still frame from that occultation. Here's the ADS-B data from American 1517. Now with some celestial theodolite observations of my own in hand, I compared the globe model to Alan's celestial theodolite method of moving the observer to the target coordinates and turning off refraction. For the globe, I used my actual location for each observation, the location and altitude of the plane, and accounted for both refraction of the plane and the star being occluded. I didn't use Stellarium. Instead, I downloaded the Hipparcos catalog and ran the numbers for proper motion, precession, aberration, and nutation myself. The resulting globe prediction of the star's elevation with refraction included was compared to the expected apparent elevation of the plane based on the ADS-B data. I plotted the distance of each airplane against the height error given by each model, and a pattern quickly emerged. This pork chop plot shows how well the globe model expects Alan's celestial theodolite to perform for a given target or peak altitude and distance. For mountains within certain distance and altitude ranges, the globe predicts that the celestial theodolite will yield results that seem to line up with a flat Earth rise over run angle. But as the target gets farther and higher, the error increases, and that's what we see in my data of airliners at or near cruising altitude. One thing we can do to better test the null hypothesis that Earth is flat is to increase the distance and altitude of the target even more, to increase the amount of curvature that should be affecting it if Earth is round, while also picking a target higher in elevation than a distant mountain to minimize the impact refraction would have. We can also cut the middleman out of the equation and directly measure the elevation angle using something like a telescope instead of having to infer the angle based on occultation timing. I now picked an even higher, more distant target, a weather balloon, just like the balloons I had been using to convert the ADS-B barometric altitudes back to the GPS altitude. I observed this balloon from the Sunshine Skyway Bridge as it floated away due east of me into the morning twilight. I measured the apparent elevation of the balloon directly using my telescope, and although it's hard to see, it's this faint little thing here. As with the airplanes, I received the coordinates and altitude from the balloon directly and simultaneously using my own antenna and RTL SDR. Now, with additional elevation readings from the weather balloons providing additional data points that you can see how the results continue to diverge from what would be expected if Earth were flat, while the globe continues to perform just as well as it had before. In the table at the bottom, the first column on the left is the measured apparent elevation or altitude above the astronomical horizon. Note the difference from the predicted flat Earth rise over run angle. And also note the target height error on the right. The flat Earth's height error climbs as high as 1.5 kilometers, and the angular error is about 0.6 degrees, 7 times higher than the amount of refraction expected by a globe for a target this far away 6 degrees in elevation. Even if you could see a star hidden behind the balloon, it would only be experiencing about 0.146 degrees of refraction, 4 times less than the error produced by the flat Earth model. By choosing a target this high up, I've removed arguments about refraction from these results, and the results are clear. The data comports with the globe, not with a flat Earth. If Earth were flat, I would have been looking in the wrong place. The balloon would have been outside the vertical field of view of my telescope by several times over. As it was so faint that only the main telescope could see it. I only located it at all because it was exactly where the globe predicted it would be based on the GPS coordinates and altitude data that I was receiving from it in real time. Jesse Path of Light provided me with some of Heffron and Allen's observations. Here's what the height error looks like for flat Earth versus the globe across the whole data set. My observations are the first ones on the left side of this graph. And here is the error in terms of elevation degrees. Again, my observations are the first ones here on the left side of the graph. I ran a mixed effects linear model on just the occultation data, not even counting the weather balloon tracking, and found that the three-way interaction of the model, target surface distance, and target altitude were highly significant with a p-value less than 0.001. The significance literally cannot read any higher here. The root mean square error was 6 times higher for the celestial theodolite than for the globe. The celestial theodolite data are actually strong evidence in the globe's favor when you properly run the globe prediction with refraction included instead of straw manning the globe. I also ran a best fit analysis without even including the weather balloon tracking data and found that for a spherical Earth approximation, the data indicate an Earth radius of about 6,375 kilometers between Earth's polar and equatorial radius and within just a few kilometers of the mainstream mean value of 6,371 kilometers. Going forward in projects where I need to know what the radius value is for the Earth, I will be using this value derived thanks to these observations, which now include my own airplane observations. Thank you, Alan. And that's the end of my intro.
All right. So you got that in 11 minutes and 50 seconds. Not bad. All right, Alan, I am going to reset the clock now. You have 20 minutes for rebuttal, and the clock will start once you do.
All right, give me 1 second. Let me switch my notes around.
Okay. And if you need to screen share, just let me know.
Yep. Let's see here. Screen sharing now.
Just waiting for it to show up on my end.
Okay. So real quick, I think I missed it, but Astronomy, did you say that you did analysis from the position on the planes or the balloons? That
Hang on 1 second. Hang on 1 second. I think your connection is starting to go south on us. Astronomy Live, are you seeing the same thing?
Yeah, he looks like a potato can, and I can barely hear him.
Alan, if you can do me a favor, if you can hop out and hop back in because the connection is going south. Because it's not even allowing me to allow you to screen share. Sorry, guys. Technical difficulties. The internet does that sometimes. God, I hate technical difficulties. And we were on a roll, too. Ellen, if you can hear us, try to hop out and hop back in. It's definitely not my internet, and it's definitely not your internet, Astronomy Live. Just give it a second here. While we wait, I'll go ahead and say that all the links that that each participant would like to share, it will be in the description after the debate has concluded. So yeah, look for that after everything is done. All right, Alan, let's try this again. You back?
Yes, sir. Testing 1, 2.
All right, much better, much better. All right, let me try that again. All right, now it's actually sharing. All right, so once again, you have 20 minutes for rebuttal, and I will start the clock when you start.
All right. Dude, Astronomy, that's awesome what you did. But when you were speaking about what you did for the flat Earth prediction, you said you did that all based on the observer-centric position? You didn't do any analysis from the plane?
Oh no, I did absolutely. I did analysis from the.
Hang on. Let's stop this here. So for this one, I would like just to give Alan a chance to. I understand that was a question, so let me just rephrase. This segment is just 20 minutes, just you, Alan, to rebut anything that Astronomy Live said. After this and after the rebuttal phases, we'll go to a back and forth. Unless you two would like to mutually agree to just skip that part and we can do a back and forth right now. It's completely up to you guys.
I do have notes for a bunch of stuff he said, but I did just need clarification on his analysis because I missed if he had done it from the position of the plane and also the weather balloon.
Okay, so you just want him to answer one question and then you'll take the 20 minutes?
Yeah.
Okay, yeah. Understood. So Astronomy Live, if you, or better yet, Alan, go ahead and repeat the question and then Astronomy Live answer.
Okay. Yeah, so did you do analysis from the position of the plane and or weather balloon?
Yes.
Okay, cool.
Okay, cool.
Well, all right, well, definitely send me all of that. I wish you had done that ahead of time, but we will, I will continue on with with the methodology that we've used. We're using fixed positions where we can guarantee 1 second accuracy on the positions of everything, which is using known mountain peaks and fixed elevations. Now, it was stated in there that we're strawmanning the globe and we're not using refraction and whatnot. When we're comparing the raw geometric intersections for what it should be, the globe is off by what they predict as drop over distance. And then what they do in every scenario is they have so much refraction that it covers the drop over distance. They take it out. So in every scenario, they're adding back in what they wanted to take out. So we're not strawmanning the globe, but when you do that geometrically, as per this theorem from Euclid, what that's doing, if we add back in 15, or if we add back, so for Pikes Peak, for example, let's say this is 13 drop over distance. If we add back in 13 for refraction, that recovers the flat Earth angle baseline. Now, when we go to this page here that I have, you can see that the time of occlusion for the globe predicted for that raw geometric intersection is 1842.04. That's the observer-centric geometric intersection angle. And this is the time that corresponds to that for their occlusion. They missed that entire intersection by almost 2 minutes and 29 seconds almost, which is how long it takes to traverse the entire arc length, which is our position. If the Earth were a globe, this measurement that has an air difference of 2 for flat Earth and 11 for the globe would look like this. When we go to the peak, we would be off in elevation by what we failed to account for, which is that 13 arc minutes of drop over distance. So our elevation at the peak, when we reference it, would be too high. And this is never addressed in any globe analysis or what have you. Everyone avoids this and only wants to use act like refraction solves this. Refraction often puts the position of the star above the peak at the time of occlusion. As Astronomy stated, his belief is that the refracted position of the star has to be geometrically under the occluding object. Well, if that were true, then in the case of Pikes Peak, for example, the star would still be above the peak by almost 2 full arc minutes, which comes out to be 10 real life seconds. So in other words, the star would have had to linger on the peak or something before it got occluded, but the occlusion happened at this time. So he would have to cut off the difference and say, oh, well, there must have just been 11 arc minutes over 11 and a half arc minutes of refraction instead of 13, even though if there was no mountain peak there, that would be the exact amount needed to explain the angle. And for things like the Novaya Zemlya effect, where the sun has been seen, with 4.9 degrees above the geometric horizon when it should have been below by 4.9 degrees, a 10 degrees of refraction is invoked to explain this overcoming of the geometric horizon. But in every case for the occlusions, that's never present. So it has nothing to do with the refracted position. And even in fact, at Lucky Peak, where we did a really close distance and 6-degree angle here, the refracted position isn't high enough to even equal the globe angle to the peak, even though the angle difference between flat Earth and globe isn't very much here. It doesn't have anything to do with overcoming the apparent position. It's all about being relative to the peak, and that's why the timings are showing the discrepancy there for what the globe predicts versus what flat Earth predicts. But then the refracted position, literally adding back in the timing difference that it would take between a flat Earth and a globe for the star to only drop half of the arc length to intersect is shown in every single measurement. So it's not that we don't account for refraction, it's that it doesn't have any bearing on this. And then when we do, it actually recovers the full flat Earth angle, which means that it can't possibly falsify the null hypothesis. None of what you've presented so far falsifies the null hypothesis, and I will have to take a look at the plane and balloon data. That sounds awesome. I can't wait to look at that. I'm so glad that you actually participated in it. Thank you. And then, so real quick, how much time do I have, Red? So there was a couple other things.
Yeah, 15 minutes.
Oh, fantastic. Okay, so even ending refraction back. You did do a fairly good analysis. I wanted to compliment you on the Steelman of everything at the beginning there that you talked about for the process. That was a pretty good, accurate representation. Much appreciated. And then let's see. Okay, so when we get into air analysis, right? This is the geometric implication for occlusion. So in this scenario for Mount Rosa, you see the occlusion was very close. It was only 43 arc minutes off at the time of occlusion. Now, this is, and you see that what this produces in terms of air for the elevation difference when we derive a triangle using only one of the other known variables in the occlusion angle, referenced by the position of the star at the peak. So remember that the globe predicts that the observer only perceives half of the arc length, so their occlusion should happen earlier. And what's happening is the full arc length is being traversed here, and that's what's and that timing delay is what is causing this angle to be closer to flat Earth every time. Now, when you do an analysis on the arc length, something that's really interesting here, like if you go to SE Varley, what you'll see is that the distance of 16 kilometers turns into 9 arc minutes of central angle, but the occlusion here based on the stars following the stellarium linearized rate for descent and time ended up being 31 seconds off, meaning the star lingered longer than it should have for their predicted model for an intersection, even for flat Earth. Now, what that caused is that the star went, instead of traversing only 9 arc minutes for the occlusion, the timing difference from that lingering equated to actually adding that to the 9, so it becomes 13 arc minutes of an arc length. But the analysis of the star's position is relative to the arc length between observer and peak. So when we do the analysis between the star's true position at the peak and the true position at the observer, it's over that same arc length, but the air difference here in measurement is going to be confounded to the half central angle relationship, because that's just the geometry of it. That's how the air gets in there. Like that's the geometric explanation for it. So in terms of that lingering effect, now they created a 4 arc minute difference on that arc length. So now we're off by 24 meters. And then the globe here predicts 22 minutes of drop. for their drop over distance. So some people would say, oh, this must mean that, globe, globe, globe. Well, no, this number only came out as 24 because the entire arc length plus an additional 4 seconds was perceived by the observer, which is supposed to be geometrically impossible on a globe. And when you look at how much the globe missed it by, instead of being off by just the drop over distance like they normally are, they're off by twice the amount. Remember, the original arc length was 9, so the curvature difference, like the elevation difference, is 4. But because it exceeded 4 arc minutes of the 9-minute arc length, they're now off by double the amount of the drop of the half of the arc length. So that's how that elevation difference comes into play when we do this geometric analysis. We're fully substantiated and backed by Euclid's theorem here for the chord tangent theorem, central angle theorem, and inscribed angle theorem. And the positions of the stars can all be verified in stellarium. And I ran the numbers for Pike's Peak here. So if anyone would want to reference that, they can reference the Pike Peak data here and see how the occlusions line up over time. So that's an extremely important aspect when going over the data, is that the significant factor here is this intersection difference, because that's what ends up, being added back as refraction for Earth curvature to supplement the timing difference to make it equivalent to the flat Earth angle. Let's see here. Like I showed earlier, when you add the drop over distance to the intersection difference, so in the case of Pike's Peak, we're off by 2 arc minutes. If we add that to the drop over distance, in this case it was negative, so it cancels out. It equals the exact amount. The difference here is in arc seconds, so it's not like an actual difference. So they're identical there. And then in every case, we get the exact match. The error difference is the initial drop over distance that the globe asserts and then has to be corrected out. And we're backed by geometric theorem on this one. So it's not that we're not accounting for refraction. It's that when we do, it doesn't falsify the null hypothesis. It actually helps our position, because they're just recovering the flat Earth angle and making it equivalent every time, to say like, oh, well, we're just going to cut off the extra 2 here and make it 11:30, and then that'll be okay. That's just the flat Earth angle, guys. The apparent angle, when you recover the apparent angle, you're losing the geometric globe. So that's the significance of that. And I think I'll wrap up on that one, because I wasn't privy to the data beforehand. So I don't have anything to say about it, really.
All right, understood. So thank you very much. That was 11 minutes and 7 seconds. Astronomy Live, I am resetting the clock right now. You have 20 minutes for your rebuttal, and it will start when you do.
All right, can you show my screen?
Yes, hang on a second. Okay, and ready when you are.
Okay. So Alan talked a lot there about geometric intersection, and he's trying to obfuscate the fact that the globe predicts based on the apparent angle of the star lining up with the apparent angle of the mountain. It doesn't matter that the geometric intersection occurred before we see the occultation time. That's one of the reasons I did this water tank experiment, to show how light refracts in that kind of environment. So you can see the laser there. This is from an outside camera looking into the tank, looking at how the laser's bending. And you can see the camera that I showed the view from during my intro. You can see it sitting there in the tank looking at this situation. So from inside the tank, you see the same situation with the light bending down. And this creates an effect where an observer standing away from that light, where that light's hitting, sees it, perceives it as a higher elevation angle. So if I go back to my intro for a second, and let me change which screen I'm sharing, or rather which presentation I'm sharing. Let's go back to this picture. So again, in this picture, this lowest simulated star here is actually geometrically below SpongeBob. And since Alan asked me a question at the start of his rebuttal, I'm going to go ahead and ask him a question before I continue with my rebuttal. Alan, would you agree that this star could possibly be geometrically below SpongeBob here?
Absolutely.
Okay, so why is there a difference between the star being geometrically below SpongeBob here, and yet you're suggesting that can't happen on the globe?
That's not what I'm suggesting at all. I'm saying that to account for it, you have to throw off the excess that when you have the exact amount, it would still be over the peak. So you have to drop that amount out and then just say, oh, it happened to be a lesser amount, which just recovers the flat Earth angle. I'm not saying that what you're showing couldn't happen. I'm saying that in every scenario where you add back in the drop over distance and then cut off the amount of refraction, you're just recovering the flat Earth angle. I'm not disputing what you're showing.
Well, then you're just saying that your method doesn't properly distinguish between globe and flat. You're saying that they generate the same prediction, therefore you can't distinguish between the two based on the data.
No, see, your prediction requires two additional corrections: one to make Earth curvature to deviate from a plane, two to add refraction to take out the curvature correction that you put in. Flat Earth just uses rise over run to the peak. We're making the consistent prediction with no additional corrections or anything, and that's how we're distinguishing it through the timing differences. Because on a globe, the observer is already deviated by half of the central angle. That's why the mountain peak is at a lower elevation, right? So if that's true, then the star only has to travel only half of the central angle to intersect with the peak. That's what was shown in the stellarium positions that I had up earlier when I showed the earlier timing for the observer-centric position. So it's easily distinguishable through the timing differences because the globe doesn't predict the full central angle, only flat Earth does.
Okay, so that was double speak. He said it both uh, isn't different and that it generates the same angle, and then claimed that actually the timing's better for flat Earth, and that globe Earth is just using refraction to try to cover up its mistakes, essentially. Now, he's admitting that, yes, this star is below SpongeBob, and he's right about that. That star absolutely is geometrically below SpongeBob. This simulates a star being visible above a mountain when it's geometrically already below a mountain, which is exactly what happens on the globe. And this is why you have to account for refraction. So let me go back to my other presentation. So can you see this now, different picture?
Yes.
Okay.
Yeah.
Great. So side-on view of the setup, you see SpongeBob here, you see the camera, you see the three stars, you see this little elastic band I tied to the same hole that third star is coming out of. I pulled that elastic band taut, and it goes over SpongeBob. And you can see how the elastic band deflects at the base of SpongeBob to a slightly different angle. This, again, proves that it's geometrically below SpongeBob, and refraction is the only reason it's visible. Here's the view from the underwater camera. The lowest star, again, just above SpongeBob, just like a star, just above a mountain, apparent position above the mountain, but geometrically, it's below the mountain. You can actually see the elastic band starting to come up and over that base, even from the perspective of the underwater camera, and the elastic band going to my finger where I'm holding it on the camera. I'm actually holding it a little too high, if anything, which is why my finger's not completely blocking the camera here. And yet, even at that angle, a little bit too high, it's already having to deflect over the base of SpongeBob. Now, when I drain the water from the tank, we see the side-by-side comparison when there was water with this refraction gradient inside the tank. And then once I've drained the water, now suddenly the two black thumb screws are the same shape because there's not that vertical compression of refraction, and the lowest star is now below SpongeBob. So this is equivalent to what happens in the atmosphere for real. Whether it would be a globe or a flat Earth, you would have to account for refraction. And on the globe Earth, when we actually account for refraction, we actually see that it's matching what we expect. And that's not because we're adding some artificial value to try to cover up what is actually caused by Earth being flat. In fact, the refraction that I computed with my observations, which again, if we go back to my other presentation, we look at the deltas, we look at the difference between what flat Earth predicted and what globe Earth predicted, it gets worse and worse as the plane gets higher and farther away from the observer. We see bigger and bigger deltas. Already with just the airplane data, we're getting up to almost 500 meters of delta between the flat Earth prediction based on the celestial theodolite and what the flat Earth expects for a rise over run angle versus the globe. And the delta, the error from the globe, is completely consistent with what we know about the certainty in the airplane altitude data that's being transmitted by ADS-B. And so when we look at this pork chop plot, the globe predicts that yes, for certain mountains at certain distances, consistent with what we get in Allen's data set, you will see very low to zero error for the celestial theodolite, and that there is no difference, which is why he's trying to appeal to, well, our model makes fewer assumptions than yours does. The thing is, my model hasn't been making assumptions. No. Let me go back to another presentation here. How much time do I have, just out of curiosity?
You're at 6 minutes, 49 seconds.
Perfect. So, yes, no, my model is not making the assumptions that Alan thinks it's making, and it's certainly not making assumptions to try to cover up some mistake caused by Earth being flat. Oh, no. Now, let me see here. Let me start this. Turns out I was doing this with ray tracing. So this is ray tracing based on the weather balloon data. It's bending the light. The first ray it shot was too low because that was based on the geometric angle, but when it passed through the atmosphere, the ray tracing caused it to bend too low. So it's got to angle up more until it finds the right angle that intersects the target. So basically it's doing an iterative ray trace solution, where it starts knowing what the geometric angle actually is, sees how far off that is, and then it iterates until it finds the angle that actually intersects the target, and it has to angle up. That angle is the refraction, basically. So I'm not using an assumed value. No, I'm using ray tracing based on actual weather balloon data for the observations. I went back and collected the weather balloon data from Alan's observations, from Alan and Heffron's observations, including Pikes Peak. That data will be available as a link in the video description as well, along with the source code to the ray tracer. So you can run it for yourself and see. And the deltas come out lower for the globe than for the flat Earth pretty consistently, except in a couple of cases where, again, the globe predicts the celestial theodolite will get almost the right answer anyway, and the delta between the two is very small. So when we look at the graph, again, of all the observations together, if we look at let me pull up the other presentation. If we look at the graph across the whole data set, that was in here. So if I show this slide, here we go. So yeah, the orange line, again, this is based on the celestial theodolite. We've got, for the airplane data that I have, as the airplane gets higher and further away, the error goes up and up. The globe, very consistent. And it's consistent even through Alan's celestial theodolite observations. All of this conducted with, again, ray tracing for the globe's refraction, not just some assumed value. And when we get into targets that are very high and very far away, we absolutely reject the null hypothesis. The balloon data here is 6 degrees over the horizon. And as I described in my intro, the delta there caused by refraction is a fraction of the delta between flat Earth and the globe. The flat Earth error is over 1 kilometer in size, and the actual angular size is 0.5 degree to about 0.6 degrees. The amount of refraction you get at 6 degrees above the horizon isn't even close to that. And for a target at this distance, at this altitude, again, the target refraction is based on that ray tracing to an actual target at a finite distance. It then, for the star, continues out till it exits the atmosphere. But for the target refracted, again, for the balloon observation, I'm measuring the elevation directly with the telescope. The amount of refraction there is only about 0.08 degrees. So that is significantly less than the flat Earth error here. This absolutely refutes the null hypothesis. And it shows that flat Earth does not comport with reality. What does is the globe, very consistently. So no, Alan is absolutely obfuscating here the fact that the globe actually predicts things the best. And when he talks about geometric intersections, he's basically just straw manning the globe, because the globe doesn't predict that the star will disappear based on a geometric intersection. It will disappear when the two apparent angles line up. So he talked about that. I also kind of wanted to go back for a moment about, he brought up Besselian elements with eclipses, which I thought was funny. I have a whole video on that here on Brad's channel, and I encourage everyone to go check it out, about how you compute eclipses using Besselian elements. His friend Shane talked about that a bit, and he could only get about halfway through the process, not understanding that you actually need the globe to be able to do that. The fundamental plane bisects the globe in that model. That's about, once you get the coordinates on that fundamental plane, you're only halfway done with the process. You then have to find out where the shadow of the moon is intersecting the globe's surface that is bisected by that fundamental plane. I walked through the steps on how to do that in that video. showing how Shane is wrecked by eclipses. And yeah, it turns out you need the globe to predict eclipses and to predict the path of totality, especially for solar eclipses. And so that's what I did. And I had challenged Shane to predict the next eclipse in the sequence. He was plagiarizing the 5 millennium canon of eclipses, and I challenged him to predict the first eclipse after the end of that sequence, which was going to be, I already figured it out myself, it was going to be in October 3001. He couldn't do it. I could, because I wasn't just plagiarizing some existing canon of eclipses. I was actually doing it myself based on the orbital elements of the Earth and the Moon, and I correctly predicted the path of that eclipse. So if you happen to be around in the year 3001, you'll see that the total solar eclipse in October 3001 follows the path that I predicted in that video. I just thought that was kind of funny that he'd bring that up. But yeah, going back to the celestial theodolite for a moment, we have very clear data here that refutes the null hypothesis, especially when you get into targets that are higher and further away. And we see that very consistently with the balloon data. So I'm going to wrap up here with a direct question to Alan on why it is that we see balloon data that indicates that this balloon was 0.6 degrees too low according to Flat Earth. The actual measured elevation was about 6 degrees. The flat Earth rise over run angle, given the distance and the altitude of the balloon, was about 6.5 to 6.6 degrees. Why is that?
All right, thank you very much. Hang on. All right, so you were done in 12 minutes and 57 seconds. Excellent. We are very good on time. So now we're going to go to the back and forth section. Alan, since you are about to answer Astronomy Live there, I'm going to let you go first. Just to make this clear, there is no time limit here. So you guys keep going as long as you guys want. And then after you guys have done whatever it is you need to do, we're going to go to questions from the audience via the super chats. So with that, Astronomy Live, if you want to repeat your question, and then Alan, you go ahead after that.
Okay, great. So I'll repeat it one more time. I measured the apparent elevation of this balloon from the Sunshine Skyway Bridge as it drifted east of me. The apparent elevation that I measured was 6 degrees. At about 150 kilometers distance, the flat Earth rise over run angle for the altitude of the balloon, which at this point was 17.3 kilometers, the predicted angle, according to the rise over the run angle, is 6.6 degrees. So the globe Earth, with refraction, again, predicts about 6.01 degrees, which is within a tiny fraction of a degree of the prediction. It's dead on for the globe. So why is the flat Earth angle off by over half a degree, over the size of the full moon in the sky, and so high that it would have been completely outside the field of view of the telescope if I'd been pointing where the globe told me to point? And that's exactly what I did, and I found the balloon. Why is the balloon too low, according to Flat Earth?
Well, I'm going to have to look at the data. It seems like you didn't, make me privy to any of it, so I can't answer any of it adequately. This is all new, and it's a different methodology from what we actually do. So it's an all new thing that I'm going to have to analyze, and I look forward to going through it. And I hope that you can send me everything that you have, especially the ray tracing stuff. So I don't have an answer for you right now. It's the first time I'm seeing the data. You definitely should have shared this if you wanted to debate on it specifically. All of my data has been publicly available for the last 38 weeks. I do weekly streams on it. So all of it's there, and you had no problem accessing any of it because you went over it and accurately represented my position. So if you want to talk about the actual data from the actual method and how to falsify the null hypothesis through geometric intersection analysis, not adding a correction into it, then I'm more than happy to do that. So one of the things that you brought up specifically and repeatedly was that we're strawmanning the globe and yada yada. So let me screen share real quick, and we can go over a couple of measurements for what I said. I'm not strawmanning anything. So let me pull this up real quick. We can look at this. So allow. Okay. Should be live.
I'm not seeing it on my end.
Give me 1 second. Let me close and reopen thing. It could be a, dare I say, Linux issue.
I'm on Linux.
Yeah. Oh, there it is.
There we go. You doubted the
Nice.
Linux too soon.
I know. Please forgive me. I've sinned or whatever.
Only this one time. Go ahead.
All right, thank you, sir. Okay, so for Pikes Peak, there's a predicted 201 drop over distance here. For the astronomical refraction added in, it lifts up 297 meters. So it completely compensates for the drop over distance as an apparent effect. Now, again, geometrically, like we went over through chord tangent theorem, that's just recovering the flat Earth baseline that's taking out what was put in as a correction. It was stated earlier that my model doesn't assume things or whatever. Well, it certainly does. It assumes that the baseline from a tangent is deviated by the drop over distance of a sphere of radius r, which is defined by the celestial sphere as well. So you can assume the equivalence between the two, and there's no difference. And because it's tied to a fictitious observer at the center of Earth, it's not mutually exclusive to bind that linear rate. That's actually what we're testing, is that 60 nautical mile per degree linear rate. When we go to distances that are extreme here, so we have 130 kilometers from Pikes Peak, I'm sorry, for North Peak, we missed ours by 13 arc minutes. The globe missed theirs by 21. That's 1,300 meters of drop over distance there, and they didn't. But it's all over the same arc length. So what happened in there obviously was the lingering, which creates that difference between the two, but still has to split it back to the globe like we looked at earlier on the SE Varley measurement. So that air difference, because the arc length of the star's position is changed relative to the original arc length, that's what produces the intersection air difference over that same arc length. So the star did occlude at the rise over run at the peak over the flat Earth angle, and to try to accommodate for that, all this refraction is added in to compensate for 35 arc minutes of drop, and with that, it would still be 3 arc minutes above the peak at the time of occlusion. Or no, wait, for positive, it would be positive is below the peak. Sorry, or no, that's negative. So yeah, for negative, it would still be above the peak at the time of occlusion by 3 arc minutes. So you talked about how the apparent position has to, be below the physical position, or even the apparent position as well. Well, if you add terrestrial refraction from that to the peak as well, the star is still geometrically over by, it's geometrically over with its apparent position by 2 arc minutes. So it's still, so in every scenario, you have to say that there was the exact amount of refraction to recover the flat Earth angle. And that's exactly what's shown in every single one of these. Blodgett Peak, there's 100 meters of drop. They assume 200 meters of lift. So every time over the same central angle. None of that is being addressed. So if you recover the flat Earth angle, you're not falsifying the null hypothesis. You're adding 2 corrections to the model. One correction for the deviation from a plane, that's the Earth curvature. That's what creates this central angle deviation proportional relationship to the chord tangent theorem. And when you add that back in, you're flattening that baseline. You're adjusting the timing difference to match what flat Earth predicts, because we predict the traversing the full arc length. So in every scenario, when you add refraction, it doesn't help anything.
Okay, so that was a lot of words to not answer my question, but okay, let's move on. The SE2 Varley, I'm glad you brought that up. The error you show there, including both astronomic and terrestrial refraction, is a bit larger than what I'm showing with my data. I get an error in terms of degrees of 0.014 degrees for this top one. This is the SE2 Varley observation, which is smaller than the celestial theodolite error. So again, globe wins on this one. The question is, which one better comports with reality? You're never going to get 0 error. You're going to have some variation, some error in the observation. With these observations, again, I am accounting for refraction as best I can based on conditions at the time, using weather balloon data from that day. But it's not like these observations were put together and performed trying to time them as best as possible, as close as possible to the actual time of the balloon launch, obviously, nor were they strategically positioned to be as close as possible to the nearest balloon launch or anything like that, right? So the balloons are launched at either 0 or 12 hours universal time, twice a day, essentially. This observation, for example, occurred at 7 hours universal time, so nowhere near the time of the balloon launch. But even so, taking that into account, I'm still able to get an error that is lower than celestial theodolite. So yeah, I'm able to show that the globe is the better fit. And when I do stats on this whole data set, what I see is very consistently and an extremely strong p-value of less than 0.001. To put that in perspective, on a three-way interaction, I'm a scientist by trade. I'm not going to wave that around as, oh, you should believe me, I'm a scientist. But I'm just going to say that in the 20 years or so I've been doing science professionally, I have never, ever gotten that level of a p-value on a three-way interaction. Granted, I work in the biological sciences where the noise is naturally higher. But because of that, I'm intimately familiar with the fact that measurements have noise in them. And so it's rather telling that the data set yields a globe result with a stat value that literally can't show any higher significance than it already does with the mixed linear model that I'm doing, and shows that the globe is by far the better model with a better fit to the data. So the natural conclusion to that would be to reject the null hypothesis. That's what we would do in science. Now, what Alan is doing is trying to obfuscate with the geometric intersection, which is not when the actual occlusion timing happens. Now, his accounting for refraction, I guarantee you, it doesn't use ray tracing, and it doesn't use the conditions that were actually present as close as possible to the observation at the various angle or the various altitudes that the balloon traveled through. Which is what I've done, and that's why I'm able to get, that's probably at least part of why I'm able to get a lower error for the globe in my measurements based on the software that I was using. So again, if we look at the target height error with the balloon, we see, it goes sky high. These observations here are with airplanes. This is with what he's familiar with occultations of stars, and even here it starts to get crazy with altitude variations from flat Earth to globe Earth, and the flat Earth error is approaching 500 meters. If the plane were actually 500 meters off of its actual altitude, planes would be running into each other a lot more often, and yet we don't see that happening. So with the balloon, he didn't give me an answer. He has no explanation for why it's so high here. But fundamentally, another aspect of all of this that is required to be able to even do any of this is to know the distances between points, the distance between the observer, the distance to the peak. Now, he's going to claim, I suspect, well, okay, I'll let him speak for himself. I won't say what he's going to claim, but I will ask him, for example, with this balloon observation, okay, so this balloon was due east of me. It was on the same line of latitude as I was here in Florida, and it was due east of me. We can go back to my spreadsheet here. I'll unhide these top rows that have balloon observations in them. And yeah, the balloon here was at the same latitude as the observer. The only difference was the longitude by that amount there. So, Alan, let me ask you, how would you find the distance to that balloon on the flat Earth? What would you use?
Would use what we're using for everything else. We would use Haversine.
Okay, so he would use Haversine. Well, that's the globe. So yeah.
Can I respond to that directly, please?
Yeah, go ahead.
Sure. Yeah, so we're using that as the radius of the celestial sphere. Distances are calculated based off of the positions of the stars. That's what the Haversine method does. Here's the Wikipedia link for a guy who made a bunch of tables.
Hang on. Let me switch this around. All right, go ahead.
Gotcha. To start referencing it. And like I said, because it's tied to a fictitious observer at the center of Earth, it's not mutually exclusive. So if we have a unit of meters as a ratio of a terrestrial meridian, and we're calculating distances between the change in positions of stars, we could use the same thing. It's not mutually exclusive. And the thing is that if it was mutually exclusive, when we do these occlusion analysis, we should never be able to exactly recover the flat Earth angle, and the optical refracted position of the occlusion timing shouldn't be such that it exactly compensates to match the flat Earth angle. That's preposterous. We should always be above it as per the chord tangent theorem, because we didn't account for it. So that's my answer to that. You say that you assert that it's the globe, but it's a numerical number that's used to use a internally consistent coordinate system that's self-referential. So I don't dispute the use of it.
Okay, so he doesn't dispute the use of it. He says it's not mutually exclusive. Let me ask you, Alan, is the North Pole at the center of your flat Earth?
Most likely, yeah.
Okay. And the lines of latitude, they're circular concentric circles around that North Pole? Is that fair to say? Okay. What's the distance between the North Pole and the equator in your model?
Well, if you calculate it out based off of latitude lines and positions of the stars, it comes out to like 6210 or something.
6210 what? Kilometers or miles?
Nautical miles, I think.
6210 nautical miles.
Something like that, yeah.
Okay, 6210 nautical miles, 2 kilometers. Let's see. Come on, Google. What is that in kilometers?
So to be clear, though, like we're debating the geometric intersection angles of the star occlusions, not distance discrepancies calculating positions of stars. Do we all agree that using Haversine, the distance to the peaks is agreeable? Like for Pikes Peak, that's 50,000.
Hold on.
Meters.
Let me. Before we run off, okay? You said 6210 nautical miles from pole to equator. Is that correct? Is that fair?
Mm-hmm.
Okay.
That's what it calculates out to be.
Okay. So 6210 nautical miles is 11,500.92 kilometers times 2. So that is the total radius, right? So flat Earth radius. Now let me share my screen.
The 6210 isn't a radius value, though. Like what you're doing is taking a geodesic. That's a curved line on the graticule. That's the longitude line's a curve. So it being flattened out doesn't represent.
It's fine.
It doesn't actually represent like the actual.
Hold on. Let me share my screen.
Okay? It's not a radius value for us.
I understand. But so I'm just trying to get back to, because I had my spreadsheet already set up. Okay, so I needed to put it in as a radius, but we're getting it back to the flat Earth. We're recovering the pole to equator value. That's what I'm actually using. Okay, so it gets back to that 11,500.9 kilometers. Okay, now I put in the latitude and longitude of the balloon here. My latitude and longitude, the balloon's latitude and longitude, using Euclidean geometry. The distance to that balloon, according to the value you just gave me for the North Pole to equator, that should be 211.417 kilometers. That's like 60 kilometers more than the Haversine. The flat Earth elevation angle for the balloon now drops because that distance has drastically increased. Now we're talking a flat Earth elevation level of 4.68636 degrees. We're talking about an elevation error of 1.32 degrees. We're talking about a flat Earth height target error now of 4.88 kilometers. So how'd that happen?
Well, it happened because you use something that's not a radius value as the radius.
It doesn't matter. It doesn't matter.
Okay. You can just put in whatever number you want whimsically. It absolutely matters. That's why
it does not matter.
Okay, if you look at my screen share real quick.
No, hold on. It doesn't matter.
Hang on.
Before you share your screen, the only reason I was
Everyone stop. We're getting a little hot under the collar right here. So let's all calm down a bit, okay? All right, so what I'm going to do is I'm going to let Alan show his screen share first, then you can go Astronomy Live. All right, let's go. So Alan, I am showing your screen right now. Go ahead.
Thank you. Yeah, you're using a flattened out longitude line as a radius. That's an improper use of a longitude line. It's curved by definition. It can't be a radius. We're using the conceptual height altitude as the radius value to put in for the celestial sphere. These two things are equivalent here. Distance traveled on Earth would be the exact same. There would be no difference using these two. So this idea of using the calculated linear distance from the latitude lines to the equator to the North Pole isn't a radius value. So I reject that premise. And we need to get back to actually talking about the Celtheo, the occlusions, right? We're not disputing the distance to the mountain peaks. So we're in agreement that the celestial sphere Haversine can be used. So why doesn't that correspond to any occlusions that are derived from that celestial sphere when using it with the globe dimensions? Why are you always recovering the exact optical angle using refraction, which turns out to be a literal geometric correction, making it, recovering the flat Earth angle? Like, why are we doing this rigmarole over you misusing a radius value? Go ahead.
All right, so let me stop the screen share there. In Astronomy Live, you now have your screen share up. Go ahead.
So once again, the only reason I was putting in as a radius value is just because that's how I already configured the spreadsheet. But all I was doing was taking that value, dividing it by 2 to get back to what I was actually interested in, which was the flat Earth pole to equator value that he just told me. So with that value in place, we should have a distance to the balloon of 211.417 kilometers. He's claiming that we can just use Haversine. Well, the Haversine uses the globe. You've accepted the globe by using the Haversine. In reality, your flat Earth does not give the same distances, okay? The distances are all screwed up on flat Earth, which is why you have to use the Haversine and use the globe, because otherwise the distance to the mountain's wrong, and you could prove it just by driving your car there. So this is why he doesn't want to use this, because it gets the answer even more ridiculously wrong. But that is the natural consequence of assuming that the Earth is flat instead of a globe. He can try to obfuscate that all he wants, but that is the fact. But okay, let's give him the benefit of the Haversine then. I come back to this again, that the balloon, even if you use the Haversine distance, has a flat Earth rise over run angle that is 0.6 degrees too high for the flat Earth, and in perfect alignment, it turns out, with the measured angle that I have with the telescope, the globe actually matches that instead. So that's a problem for you, and yet that problem is a relationship of the distance of the balloon. Would you agree, Alan, that this is naturally going to happen the further I look at a balloon, and that if I look at a balloon closer, that the height error is going to come down? Would you agree with that?
I'd have to see it. Like, what you're proposing, like I said, is all new stuff. It's a different variation of our method. I'll have to be looked at and carefully considered. Like, and honestly, I'm not like super opposed to it, like off first gander. So I will definitely look at it and see, get back to you on that. But that's an entirely separate debate. The celestial theodolite that we're talking about is the geometric intersections of terrestrial features, such as a mountain peak and the stars. So it's a slightly different topic. I would love to come back to this on a separate debate or something, but we should be debating the data that we're all familiar with over the last year. That's been publicly available for everyone. I can't really comment on this that much.
So he doesn't want to talk about my data because it's real bad for the flat Earth. I get it, but sorry, if you can share my screen again, Reds.
Well, what's really interesting about your data is that you've had it this whole time, didn't propose it to me, didn't say anything, didn't say, hey, I want to be proposing some new data. Do you want to look at it? You're using it as leverage of me not knowing it. And then me saying that, I need to look at it and to consider it. You're saying that that's like a weakness somehow. That's preposterous.
So this data is pretty fresh, actually. So the balloon data, for example, we got this month, and Reds can vouch for that. The thing is, if your model is robust, you should be able to explain the data. You should be able to take a look at it. And I encourage you to take a look at it and come up with an explanation for why this balloon seems to be 1.6 kilometers, almost 1.6 kilometers too low, according to Flat Earth, because that's the height error, 1.571 kilometers. And I'm asking you, if you think, if I were to go to the balloon and get much, much closer to it, would this height error come down? Would it seem to come into alignment with globe?
So I noticed that instead of actually debating the celestial theodolite, you introduced a new method on the fly here, first time revealing it to me, and then keep asking me questions about data about it that I'm not familiar with.
It's a distinction without a difference.
So real quick, if you want to talk about the celestial theodolite and the geometric intersections and adding refraction back and how that recovers the flat Earth angle, I'm all game. If you want to discuss a new thing, send me all your stuff, and then we'll reschedule a follow-up debate. I can't comment on this right now.
Again, the geometric intersection thing is a straw man. The globe doesn't predict that the occlusion will happen at a geometric intersection. It predicts that it'll happen when the apparent angle of the target, whether that be an airplane, a balloon, a mountaintop, matches the apparent angle of the star. So it's a distinction without a difference. I'm cutting out the middleman of having to do this based on timing by directly measuring the angle. But celestial theodolite fundamentally is about trying to get that angle. I'm just directly measuring the angle. So he won't answer. But
hold on, don't interrupt me. It's a completely different methodology, bro. We're using timing intervals to measure the angle, not assuming
to measure the angle
directly.
Yeah, to measure the angle. It's a distinction without a difference. We're getting to an angle.
Over two. You're doing a different method, though.
It's a distinction without a difference.
I mean, says you.
Yeah,
says a guy who did a different thing.
I did the same thing as well with the airplanes. I did it with timing airplanes, remember? So I timed occultations of stars by airplanes and saw the same relationship.
And do you remember what I said? We're going to have to take a look at that. It's new data. It's a new thing. That's all that can be ascertained from that.
Yeah, so how's that coming with your response to Earthly Skeptic, by the way?
Let me butt in here for a second. All right, so let's hypothetically just say that we would want to, or let me rephrase. Let me try again here. It seems to me like you're wanting to have another debate in the future. Is that where we're going with this, Alan?
If he wants to go over the data like in a fair manner, where I'm aware of what's going and what's being presented, yeah.
Okay, let me ask you this: what would be? I'm sorry. Go ahead.
I said everything I've been doing is publicly available for the last 38 weeks.
Okay, so now, of course, this is just a guess here, but how much time would you guess that you would need in order to go through the data and to be confident that you know everything that you need to know about it?
I couldn't tell you. That would depend on the individual, but he was so confident in it that he decided to debate me on it. But he offered the challenge of it. So I would assume that he did his homework and knew about this intersection stuff. He went over the intersection comparisons in his intro, so I know that he's aware of how the methodology works, but then to not go over any of the data or acknowledge it is preposterous. To say that we're strawmanning the globe with refraction, we account for refraction, and when we add it in, it recovers the flat Earth angle. So that's not, doesn't help at all. He just keeps saying that we're strawmanning it.
So what I'm hearing is that if we were to schedule another debate in the future, we would have to wait for some sort of scheduling from you after the fact. Is that fair to say?
Yeah, I could probably knock it out in like a month or so.
A month. Okay. That's why I wanted. So somewhere around a month. I'm more than happy to set that up again. But Astronomy Live, to that question, new data and that kind of thing. When you came up with this, how old is this data? How long have you had it?
So, like I was saying, the data, some of this is extremely fresh, as in this month, and it's taken me until basically now to complete the analysis of it. Literally, I've been working on it this week, making sure it is all correct. So the data is available in the link that I gave you, Reds, to post in the video description, including the source code for the ray tracer. And you can run it yourself. It's just a Python script thingy. And you can recapitulate the output, which I've got here. Again, some of this is extremely new. So the latest observation was February 9th, and it took until now to complete the analysis of that data and put together this presentation.
I got you. Okay, so what I'm hearing here is that Alan doesn't want to address it because as of right now he's just not familiar with it, and it looks like with that we are at an impasse as of right now. So what I'm going to do is I'm going to call it here. Let's go ahead and go to questions from the audience, and we will go from there. So for the first super chat, which I guess isn't really a question, it's more of an advertisement, but we'll go over it anyway after show on Yerba Mate Talks. Well, thank you. Okay, so Earthly Skeptic for $5. Thank you very much. Alan, How does raw geometric intersection, in parentheses, with zero optical phenomena involved, cause Polaris to be invisible south of the equator? Where does the star go?
Out of your field of view. You have a limited vision. You don't see forever. That's it.
Astronomy Live, do you want to say anything for that?
Okay, well, yeah, out of my field of view. How do you get a rise over run angle of 0 for Polaris?
You have a radius of vision. Things you see are.
Oh, he's changing it. Oh, interesting. Okay.
Yeah, I misspoke when I said field of view. I meant it's outside of your radius of vision. As you get further away, things at the end of your radius of vision will curve down to the horizon. That's all it is. It's an optical setting, not a geometric one.
Alan, how far away is Polaris?
What do you mean?
According to your model, how far away is Polaris, roughly?
Oh, for the conceptual model that I showed you for the use of Haversine, we set the altitude to the same as the Earth's radius, the same way that the Earth does for celestial navigation.
Okay. What would you say if I said that I'd measured the distance to a geostationary satellite at something like 22,000 miles?
Say that again.
What would you say about me seeing a geostationary satellite that's about 22,000 miles away?
Well, I have contentions with the actual altitudes of the satellites because there are timing corrections involved in them. So I couldn't say for certain.
And see,
but I would expect, though, that it would be internally consistent with the coordinate system because the corrections that they make are timing corrections to the internal clock when it passes two GPS stations. So if there was any sort of data cooking or whatever, it would come out to be internally consistent. So.
Well, see, I'm not relying on the internal clock of the satellite. I'm measuring the distance myself with two telescopes. Parallax. Two telescopes far apart, finding the parallax to the satellite, determining what the distance of that satellite is with simultaneous observations.
Oh, I see. Yeah, so for that, I would say that that's an optical measurement. That's just optical effects. So plotting that is going to be internally consistent because the coordinate system itself is based off of that same radius. So
optical effects like refraction, right? That is it internally consistent, or maybe I'm basing it on weather balloon data where I'm ray tracing it based on the actual atmospheric conditions.
Are you aware that I'm not denying refraction exists? And what I'm saying is that it comes out to be a literal one-to-one geometric correction for the occlusion timings to offset it to make it match what Flat Earth predicts for the full central angle.
See, right there, he's attributing motive to it. That doesn't exist. There's no motive to it.
Can I show my screen real quick?
Sure. Hang on a second.
Whether or not a quote unquote motive exists, geometrically, every time the refraction amount has to be cut off exactly to match the flat Earth rise over run angle for the occlusion. That's exactly what happens. That's not a motive. That's just what's happening as prescribed by the refraction corrections for the formula that are used when you're 10 degrees below the horizon. And for the record, the refraction formulas are not derived off of any experimental evidence. They're derived from watching circumpolar stars, and then they take the position of where they observe it versus where the position it should be in their coordinate system, and they say that's how much refraction it should be. So that's how we ended up with this curve-fitting scenario where at these angles to the horizon, the refraction amount exactly matches what the amount needs to be to have it still be visible and not be occluded by Earth curve. So when you talk about geometric intersections is a straw man of the globe, it's the baseline for when an object should be geometrically occluded by Earth curve. Like when the sun hits 0 on the celestial coordinates, it's at the equator. That's when it starts to get occluded by the Earth curve for you guys. That's the baseline for it. And then you say refraction changes the actual setting time. And what I'm saying is when you add the refraction prescribed in for these stars in the same way for that 0 baseline to start with, for when it should be occluded for the globe, it literally recovers the flat Earth geometry. All you've replied with so far is just pure rhetoric. You haven't addressed this at all.
Oh, I've
at one
absolutely
point,
addressed.
at one point in the debate, you went on to
Can I
monologue
respond
about
yet?
Shane for 5 minutes.
Hang on one second.
Oh,
Okay. Astronomy Live, I see that you might be screen sharing something. Do you want me to
yes.
show it?
Yes, please.
Okay, let me bring that up, and you may go.
So he just said, I heard him say it, that refraction isn't based on experimental evidence. It absolutely is. And it is, especially in this case. All of this data where the globe is taking into account refraction is absolutely based on experimental evidence. It's based on weather balloon data from each one of these observations. I excluded observations if there wasn't a valid weather balloon, okay? There was only a few of them like this. But for example, if the observer happens to be lower in altitude by a significant amount than the nearest weather balloon launch, and the nearest weather balloon launch is, hundreds of miles away, that's not valid. So we're just not going to use that. I used exclusively experimental data to calculate for refraction here to find the prediction and the error, both in my observations that he doesn't want to talk about and in his observations. And guess what? The globe is better, and the globe ends up fitting far better with lower error. Here's what he said about that, by the way.
How much non-flatness would the celestial theodolite angle have to show in order to refute the null hypothesis, or is it irrefutable, like unfalsifiable?
No, as I said earlier, if these air offsets were reversed, the Earth would be a globe. It would be the direct implication. The null hypothesis would be falsified if the airs were reversed. It would be so goddamn conclusive, I would be here arguing against all the flat earthers.
So, according to Alan, he should be arguing against all the flat earthers now after tonight, because even just looking at his observations, the globe error is lower. Congratulations! Turns out Earth's a globe. And furthermore, as far as geometric intersections go, again, I'll show this screen again. The prediction isn't that the star will disappear when it's geometrically obscured. It doesn't matter what the geometric intersection is. It doesn't matter when that star is occluded geometrically. That's not what's going to determine the actual occlusion time. It's going to be based on the apparent position of the star because of refraction, just like we see in this water tank example. When water is in the tank with a significant salt gradient producing a density gradient, and you see that bending of light, you see the vertical compression of the black thumb screw, just like you would see with the moon or the sun low on the horizon, we see that the star is visible above old SpongeBob here. And then when we get rid of the water, oh, suddenly that star is not visible anymore. In fact, you can even see the seam at the bottom of the tank down here. That black seam is risen partially above SpongeBob here. That's how significant the refraction is here. So yeah, refraction matters, and you have to take that into account. By not taking it into account and by focusing on a geometric intersection, you are by definition strawmanning the globe and continuing to lie about it.
All right. And Alan, I'm going to give you the last word on that, because then we got to get to the next super chat. If you can, try to keep it short, but, say what you got to say.
Yeah, let me screen share real quick, because there's actually a lot to go in there. And playing a voice clip out of context is one of the grossest things you can do in a debate. What I said was talking about the geometric intersection comparisons, and your data isn't even doing that. You're doing refraction apparent positions, completely separate thing. So to use my quote about geometric intersections and to apply it to a different data set and accounting for not geometric intersections is a preposterous thing. Now, you keep saying that when the apparent position is lower than the object, that's when it gets occluded. But in no case have you addressed that in every scenario at the time of occlusion, the apparent position for the amount of prescribed refraction is over the peak that's predicted for the globe. So it would result in the star lingering above the peak. None of that ever happens. That hasn't been addressed at all. You keep saying that I'm not accounting for it. To account for it, not only am I doing that, but you have to also cut off the remaining amount and say that it just fixed the 11 arc minute difference to match the timing offset, which recovers the flat Earth angle. So you're proposing using the optical, what we see, as proof of the globe rather than the geometric when you use the refraction positions. So if you're 2 arc minutes above the peak, then that's not an occlusion. You would have to wait 10 more seconds before it occludes.
Can I respond real quick?
Actually, no, you can't, because we got to get to the other super chats. I'm sorry, Astronomy Live, please forgive me. So next super chat again from Earthly Skeptic. Thank you very much again, $5. Alan, you say a line from the center of a circle to a point on the circle on a flat plane is not a radius, question mark. Come on, don't know Euclidean geometry, question mark. Go ahead.
It's a flattened out line on an AE map is a longitude line. It's part of the graticule. It's a spherical coordinate system. It's curved by definition. A radius is a straight line. They're definitionally different things. Not being able to differentiate that is not my problem.
All right. And Astronomy Live, do you have anything about that in particular?
Not that in particular. I'll leave it. It's fine.
Perfect. I appreciate it. Thank you. Okay. Again, from Earthly Skeptic for $5 more. Thank you again. How much would the star's angle change if the distance to the star is off by 6 kilometers? Show a calculation for 39 Aquarii / Pikes Peak. And just so that we're clear, it's 39 AQUARII because I butchered the pronunciation of that.
You're good. What was the question? He wants me to add 6 kilometers to the measurement. Is that what he said?
What I will do is in the internal chat, I'm going to copy and paste it right there. How much would the star's angle change if the distance to the star is off by 6 kilometers, question mark. Show a calculation for 39, whatever the fuck the star's name is in Pikes Peak.
Gotcha. So if we just add a 6 to the 50,000, I think that's not going to change the angle. It would change by one arc minute per kilometer, right? Like, or something like that. So like 1 nautical mile per kilometer, or 1 nautical mile per arc minute. So I don't know, whatever that would be. I'm not sure the purpose of the question, what it's supposed to show. The change would occur on both models. I don't know. I don't understand the point. Like, what he's trying to get at.
All right. Astronomy Live, do you have anything to say in regards to that question?
I'm wondering if he meant to say the distance to the peak instead of the distance to the star, but I don't want to assume for him.
Understood. If that is what you were trying to ask, you can always ask it again, or rephrase it, and I'll find it. Maybe, kinda. No promises. Unfornicated for $5. Thank you so much. Alan, do you still maintain the claim that Star Mountain Observer are in geometrically straight line at the time occlusions are observed?
So the observer would see the apparent position, but the geometric alignment at the time of occlusion, when you add the arc length back, that is the implication. It makes a congruent triangle to the peak. And on a globe, we should be off by the elevation that we didn't account for. We should be above the peak by 13 arc minutes in the case of Pikes Peak. Like when I showed earlier, since I have it up, let me just show it real quick. So this is what was measured geometrically. And then if the Earth were a globe, if we change it to what the globe, if they had their ideal intersection, it would reverse that. So we would be off by 13.
All right. Astronomy Live, do you have anything to say in regards to that?
The implication of what he just said is that he's strawmanning the globe by saying that when the geometric lineup happens between the peak and the star, then yes, the star should disappear even though the apparent angle would be higher than the geometric angle. So it would just vanish in the sky well above the peak by whatever the amount of refraction is. The refraction difference between the peak and the star, obviously that doesn't happen. But that's a straw man of the globe. That's not what the globe predicts. The globe predicts that the occultation happens when the apparent angle of the star matches the apparent angle of the peak. And if you share my screen real quick, again, looking at the elevation angle error between flat Earth and globe, the globe oscillates on either side of 0. The flat Earth oscillates, but a lot more. The error is higher, both positive and negative, on the celestial theodolite method because it's broken. It doesn't work. It doesn't match reality.
All right, and we're going to double back to a previous question because there was a typo. So thank you very much for retyping it. I found it again. If the distance to the Pikes Peak is erroneous by 6 kilometers, how much would the elevation angle to 39 Aquarii change?
Well, it's not erroneous. It would change it by whatever the nautical mile per arc minute comes out to be over that. So it would change it by that.
All right, understood. Astronomy Live, anything to say in regards to that?
Not really.
All right, sounds good. All right, for $5, DP debunks. Thank you very much. What if Astronomy Live renames the planes/balloons as mountains? Will that help? Because that's basically what he's done. It's not that hard. So Astronomy Live, I guess what he's trying to say is what you did is directly analogous. Would you agree with that?
Yeah, I mean, so I specifically did the airplanes thing, right? Making sure to do the star, catching them going over stars, because I knew, I could have done this with just astrometry, right? And measured the position of the plane over multiple points in the video. Would have given me way more data points, would have looked more impressive. But he would have objected to that because, oh, it's not in front of a star in that moment. Okay, fine. Here, I'll find you some that it's in front of the star, specifically to address that comment. And sure enough, even just based on that data, yeah, the celestial theodolite starts falling apart when the plane gets, significantly far away at a high altitude. But then to address something else that he's been asked to do for a while now, he's talked about 38 weeks he's been doing this. Well, for a lot of that, he's been asked, just measure the angle to Pikes Peak directly. Use an actual theodolite and measure the angle to Pikes Peak. See if there's globe drop, So, okay, let's do that, but let's also pick a target that is significantly higher than Pikes Peak, significantly farther away than Pikes Peak, where atmospheric refraction is less of a factor, so we don't have to be worried about that so much. And let's see which one holds up. And for that, we have the balloon. Again, about 150 kilometers at its greatest distance in this video, and measuring its position over multiple points in time, we see, oh, look, the trend continues, and we've directly measured the angle. The only difference here is he's trying to get to the angle using occlusion timings. I'm just skipping straight to it here, which is what he's been asked to do for a while now and hasn't done. Well, I did it. And look, it's a disaster for flat Earth. It matches the globe, and it absolutely contradicts flat Earth. It absolutely refutes the null hypothesis, and I'm curious to see where he goes with that. Again, the data will all be available in the video description. The source code is available at the GitHub in the video description. Happy to have another discussion with him later once he's had a chance to review it. But again, this data is fresh. I literally was working on this right up until yesterday, getting all of this prepared and ready.
All right. And now for you, Ellen, same question, but let me just ask you directly. Do you believe that the balloons and the planes is analogous to the peaks of mountains?
It certainly could be. We need to go over certain aspects of like how he determined, the position and stuff over time, how he can guarantee 1 second accuracy over it. There's things to discuss over it for sure. It could be. Like I said, when he initially proposed it, I got really excited because I thought it was really cool, and I look forward to going through it.
Understood. All right, Earthly Skeptic for $2. Thank you very much again. Why didn't you include radius of vision in the celestial theodolite?
I did when I said that I was deriving distances based off of a celestial sphere with radius r. That it's a conceptual model that represents your radius of vision.
Astronomy Live, do you have anything to say in regards to that?
I'm sorry. He's basically saying that it's going to look like a globe, guys, because of radius of vision. It's going to look like a globe, and it's going to match the Haver sign. So when you're supposed to be, in South America and you can't see Polaris, that's why. It's not because Earth's a globe. Totally not because Earth's a globe, guys.
Well, on the reverse, you're actually saying that it optically looks like a globe while recovering the flat Earth angle geometrically. So you're saying it's geometrically flat, but it looks like a globe. That's actually your position, not mine.
It doesn't look geometrically flat to me.
Yeah, based off of not doing a geometric analysis. Unlucky.
Again, if you take out the refraction here, the refraction is a tiny amount of the delta here. Even if you acted like this was just a purely geometric angle and you disregarded refraction, well, you still got a huge problem because globe still beats flat Earth by a handy margin.
Oh, if we look at this new data set using different methods and stuff, we can... Come on, guy.
Direct measurement of the elevation angle, which is what you were asked to do.
That's not what we...
And
that's not, has nothing...
It absolutely has everything to do with it. You're trying to get the elevation angle.
First of all, just looking and taking the measurement of the optical angle is self-referential. That the whole coordinate system, everything is all based off of what it appears to be. We're actually geometrically testing it with occlusion timings. You're pointing at an optical measuring device.
I'm pointing at an altitude circle that has degree markings on it. It's a circle, and it marks off the degrees. You're claiming it's self-referential? No, it's not. This is an elevation measurement directly with the telescope. It's not self-referential, okay? And if I look at this tells me the elevation of what it's pointing at.
The optical angle that it's going to be is going to come out. That's the self-referential part. It's going to be it's going to match exactly the optical angle to it.
So you're saying that, oh, because of refraction, it's going to match. Well, I got news for you. Refraction here is a tiny portion of the error. So even if I disregard refraction and treat it as geometric with these observations, you still got a huge problem. Yeah, it makes the globe result a little worse because refraction actually does matter. But even if I disregard it, oh, you still got a big problem here. Yeah.
The big problem is didn't use our method, use different stuff, introduced a new thing. So it'll take time to go over that and get back to you on it.
It's a distinction without a difference because you're still trying to get to that angle. You're just using timing of stars behind the object to try to find the angle. I just measured the angle directly. As you like to point out about the model with fewer assumptions, well, guess what? Doing it this way with the telescope and directly measuring the angle, yeah, that's got fewer assumptions. But that's not why I'm saying this is superior. I'm saying that this is superior because it's a target that is higher in altitude, further away, where the two models are going to predict a bigger difference. And they do. And what we see is the results match the globe.
I can't wait to do the follow-up analysis and look and see your data.
All right. Excellent. Let's go ahead and move on. Also, someone said in the live chat, at Ritz Redick, you don't need to emphasize the tick at the end of my username. YouTube just didn't have Earthly Skeptic available. Okay, well, thank you for that correction. I will be sure to emphasize, to put even more emphasis on it just to be annoying. So with that, let's go ahead and continue. Deplorable Ilk for £5 says, can Alan explain how Haversine and flat Earth distances are the same? His flat Earth map is the AE map, is it not? Question mark.
Well, the AE map is just a projection of the graticule, which is a spherical coordinate system that is latitude and longitude, which is dependent on the position of the stars at the first point of Aries, and then deviations from that are referenced to determine, how the star changes over distance. There is no difference in what flat Earth would predict. And if you could show my screen real quick, I had the equivalent there showing the same thing for a drop of the stars, assuming the same altitude. So using the Haversine is just the change in position over stars. That's what it's calculating. That happens on both models. One is assuming that it's a linear rate though. And when we get to the horizon, that's what we find, that it's not a linear rate. The intersections show that there's a deviation from the celestial sphere. And geometrically, for the true positions, there can't be any deviations like that because the globe is dictating the change in position of them. So there shouldn't be any discrepancy for the true positions in the way that it's showing up in the occlusions if they're truly following that linear rate. It's just used as the baseline for the calculation. And when using it, with respect to the coordinate system itself, it'll always be internally consistent. So.
All right. And Astronomy Live, unless you have something else to add to that, I'm going to get to Slice Arcane next.
No, that's fine. You can just go to Sly.
Okay, Slice Arcane for $6.66. Nice. He says the following: what flat Earth angle, question mark, in all caps? I presented a similar argument regarding angles to Alan at his request, and he went silent weeks ago. I guess the question is, are you planning on getting back to Slice Arcane anytime soon?
Absolutely. I told him specifically that I don't get Twitter notifications, and that if he wants me to address something directly, all he has to do is DM me. He's never messaged me once. I have no idea what he's like. What I'd be happy to look at it, but I don't know what he's referring to. And I told him the best way to contact me. I even invited him to our Discord, and he said, no thanks. So
Understood. All right. Earth is Life for $5 says, Alan, where are the stars 6 hours after they've been occluded according to Stellarium?
according to Stellarium, they would be under the globe.
All right. Astronomy Live, anything to add to that?
No.
Okay, cool. Earthly skeptic. I'm sorry, hang on a second. Earthly skeptic. Did I do it right? Hopefully. Alan, Haberstein, yeah. All right, let me try that again. Jesus Christ. Okay. Haberstein calculates that longitude converge, not diverge, south of the equator. It also calculates South Pole has 0 diameter. Do you agree? Question mark.
It is a conceptual model, and when both hemispheres are represented, that's what it would calculate out to. I agree that that's what it calculates out to.
All right. And Deplorable Ilk for £5. Again, thank you very much. I really do appreciate it. If Alan is so upfront and honest, why does he block people on Facebook who challenge his claims?
I don't have a Facebook, so I don't know who that person is or who they've tried to talk to me. I run a show every week where people can come and talk about celestial theodolite stuff, raise their contentions, etc. It's hosted on the Earth Awakenings Discord. So I don't know who that person is. They could try contacting me on Twitter. Sometimes I get the notification, sometimes I don't. But just follow me and send me a DM, or you can come by the Discord. It's discord.gg/ethercosmology.
And you're okay if I post a link to that in the description?
Sure. Yeah, everyone is welcome. There is a code of conduct. You can't come and just endlessly argue over nothing. But it's more like a research focused place. So that's it.
Understood. Okay. So what I'll do after the show has concluded is I'll go ahead and put all these links down below, which will include a link to that Discord server. I believe those links expire after a certain period of time, if that's how it works. Is this one of those links?
No, it's permanent
one. Perfect. Okay, cool. That means I don't have to update a damn thing because I am lazy. Okay, so Flatus Earth for $9.99 says the following. Alan, in your assumptions, I screenshotted a flat Earth dome height of 6,371 kilometers. How does this contrast with Space is Fake? Question mark. No spaces there. Astronomy Live, did you catch the Freudian slip of motive?
The Freudian slip of motive. Not sure what I mean by that.
Yeah, neither do I. So, Flaudius Earth, I'm just going to skip that part. And also because I can't speak for some fucking reason right now. That is my fault entirely. But let's revisit the first part. Alan, in your assumptions, I screenshot a flat Earth dome height of 6,371 kilometers. How does this contrast with Space is Fake? I'm guessing that's a user on Twitter.
Yeah, I'm not sure. I think his question, though, was how do we come up with using the radius value? You can derive it just from the change in position of the sun or moon over distance and derive the slope of that and get pretty much the same radius value. So if that was kind of the question, then that's the answer. If that wasn't the question, I have no idea.
All right. Understood. Fair enough. Let's go. Beasticles, if that's how that's pronounced, for $9.99. Thank you very much. Can you go over one observation and show how, one, where the globe is strawmanned, and two, can Astronomy Live explain celestial refraction and how it's incorporated? Question mark.
Sure.
So that's for you, Astronomy Live. And to make sure that it's not missed, I'm going to copy and paste the question in the internal chat.
Okay. So if you can share my screen for a moment.
Yes, let me do that real quick.
So again, the straw manning comes in that he keeps talking about geometric intersections. That doesn't matter. That's not what the globe predicts for when occultations and occlusions of stars by mountains or other objects will happen. It's when the apparent angle of the object matches the apparent angle of the star. Now, in terms of how I'm calculating celestial refraction, that's based, in my case, on ray tracing, based on weather balloon data taken from the night of the observation. So I grab the weather balloon data, I get the profile for the temperature, the humidity, the pressure at the various altitudes the balloon's at, and I'm using that to conduct ray tracing through that atmosphere and see how well that matches with the observations. And it ends up matching quite well. The error floats around zero. The statistical significance is extremely high, less than 0.001 in terms of the three-way interaction between the model, whether that's flat or globe, the distance of the target, and the height of the target. Those are all highly, highly significant because, again, if you look at the pork chop plot, the globe predicts that, yes, celestial theodolite looks like it'll work pretty well around, low altitudes compared to a weather balloon, or distances that are lower than, say, 150 kilometers to a weather balloon. And when you get into those kinds of distances and altitudes, things get real bad, up to 0.6. Well, guess what we saw with the weather balloon? 0.6.
And to the second part of the question, which is, where is the globe strawmanned? I'm assuming it was when Alan was going over his presentation. There was a part during that presentation where you said that Alan was strawmanning. Can you highlight exactly what was being strawmanned and how?
Oh yeah, all throughout he keeps talking about geometric intersection and trying to make that the argument. By its nature, that is the straw man. When he complained about that clip I played of him saying that if the errors were lower, he would be a glober, he's saying that because he's trying to strawman the issue to be geometric intersection, and that if the errors were lower only under geometric intersection, then he would be a glober. Well, that's a straw man of the globe. The globe's not predicting that it should work right if you're trying to use geometric intersection. You have to use the apparent angle. The apparent angle does match. And if you get into targets and distances that are quite high, you can get to the point where refraction doesn't even matter that much. You can take it out and you start looking at observations like this. Even if you exclude refraction, the globe's still going to win by a country mile. So by all rights, he ought to be a glober tonight, and he's not. That's because he's dishonest and he's strawmanning the globe.
All right. And Alan, I'll give you a chance to respond to that. Go ahead.
Dude, framing my position as being dishonest when I haven't had a chance to look at your actual data methodology used to confirm everything is insane. And it shows a lot of weakness. Now, if you can bring up my screen real quick, I'd like to show the refraction corrections. So the question specifically was about astronomical refraction and regards to how they determined the values for astronomical refraction from a paper here from, from this Willis guy, from John Willis, A Determination of Astronomical Refraction in Physical Processing. What they did to get the refraction values is they watched circumpolar stars at low elevation angles and just calculated where it should be versus what they observed. And then from that came formulaic outputs where at the lower elevation angles, based off of the air density from their circumpolar observations, they come out with these formulaic outputs. Now, when we compare the refracted position in every time, it geometrically recovers this the flat Earth angle that I was showing earlier with the tangent chord theorem. So the position is, it optically looks like a globe, but geometrically it's flat. This is never addressed in any of the debate so far. It's always about different things and then introducing a new methodology, which was already stated to be admittedly different, but accomplishing the same goal, so therefore indistinguishable. Absolutely not. One's using timing intervals to measure physical geometry, the other is using apparent angles. So like I said, I will look at your data and go through it, and I will see if you properly did the flat Earth predictions, and we'll go through it from there when we get to it. So framing it as being dishonest is, insane at this point. I can't agree to look at your information any harder than I already have.
Okay, so yeah, it is, you are being quite dishonest because you know for a fact that I'm not doing it based on circumpolar stars. I'm doing refraction based on ray tracing from the weather balloon data. So to answer the question from the super chat, that's how I'm doing it. I'm doing it based on experimental data from the weather balloon to basically determine what the refraction should be based on the actual conditions at the time of observation from a weather balloon as close to the observation as possible. And what we see when we do that is we see errors for the globe that are lower than that for celestial theodolite.
All right, I'm going to go on to the next one, and it's going to be from Brian Peck 108 for $5. Thank you very much. Considering you also use the Bislin model for light paths, you're off by dozens of degrees at minimum, aren't you, Alan? Question mark.
I have no idea what that even means.
I'm guessing what they're, this is purely an assumption on my part, and I could totally be wrong on this, and that's okay. I acknowledged it. But I think they're saying, is there any overlap between the Bislin model and the celestial theodolite? Is there any overlap? Is there any information that both of these things agree on? Like, is there a data point that you could show with the Bislin model that would agree with the celestial theodolite?
I don't know that you could put in specific data points into the Bislin thing. So I don't know. But visually, it just represents the conceptual model of the observer-centric observer, and how he would see in a limit of vision with respect to objects circling above him and how he would perceive it versus where they are in 3D space. So, conceptually, it's used for that, but I don't know that you can plug in specific data points like that.
Understood. All right, for £5, deplorable ilk says, if optical angles are self-referential, how does or why does Alan use optical angle measurements?
We use a timing interval when the star was occluded in reference where it should be at that time, using the baseline of the linearized 60 nautical miles per degree at sidereal time. So,
all right, Astronomy Live, do you have anything to say?
Yeah, he's trying to infer the angle, and what he doesn't realize is the optical angle is what matters here. It's about the apparent position of the star and the mountain, and he keeps referring to the geometric intersection, which again is a straw man of the globe. That's not when the occultation will occur. So he's trying to infer the angle based on the timing, but ultimately what he's actually producing is the time that the star was actually occluded, which is because of the apparent position of the star and the mountain.
All right.
Okay.
Alan, go ahead.
And real quick, let me just add to that. That's not true at all, because in every case where the star is still above the peak, there's no lingering. So that's not the actual amount of refraction. You have to literally cut it off to be exact. You keep not addressing that while simultaneously saying that it would still be above it. When we reference any measurement, though, where it's still above the peak, there's no answer to it. It just remains silent.
Again, if you show my screen,
Yep, hang on. I'm getting to it.
The globe error oscillates on either side of zero. There's obviously going to be noise in the data. Sometimes globe predicts the star should have already set. Sometimes the globe predicts the star shouldn't have quite set yet. But in general, the point is that the error on average and with the root mean square error is lower for the globe. Again, the root mean square error for the globe here is 6 times, the flat Earth error is 6 times the globe error. Okay, and that's with me excluding the weather balloon observations he doesn't like, right? That's just looking at the occultations of the airplanes and the mountains. Put all that together, the root mean square error of the flat Earth, the celestial theodolite model, is 6 times higher than the globe. And the globe isn't just like, I guess he's trying to act like the globe always shows the star as on one side of the mountain, like it's still above the mountain and we cut it off. No, the error fluctuates on either side of zero here when you properly account for it like I have.
If the error fluctuates on either side of zero, you're rounding it off to be exactly what the occlusion angle would be for flat Earth over that timing difference. You're basically delaying the occlusion with refraction, and it just so happens to match the flat Earth angle in every single case geometrically. So you're arguing for an apparent globe versus a geometric globe, which is unfortunate, because if the globe isn't a geometric fact, then it's not real.
Again, he's ascribing some motive there that doesn't exist. This isn't biased data. This is based on weather balloon and ray tracing data. So it is what it is. It falls where it falls. And where it falls is the globe has far better predictive capability and comports with reality better than the celestial theodolite.
All right, we're going to move on. CK, thank you very much for $4.99. Actually, before I get there, let me go ahead and say the last super chat I see is from Beasticles for actually, no, scratch that. It's from Deplorable Ilk for £5. And so here's the thing. I love money. Money is great. Money is actually the answer to all of my problems. Any problem that I have can instantly be solved with money. I'm going to ask you to stop giving me so many goddamn super chats because we got to get to the end of this shit at some point. Okay, so Deplorable Ilk for £5, just underneath from Jess for another $5. Those two super chats, I made notes of it. Those are going to be the last super chats that I read. So if you send any more super chats, you're just wasting your money. Now, don't get me wrong. I like money. If you wish to give me money, you can go ahead and do that. Just know you're not going to be getting anything for that money. You can probably spend that money on something else. So fair warning, I'm stopping at those super chats. Anyway, moving on to CK. Alan went live 30 minutes, I'm assuming, ago, and clocked out early. We all know why. Astronomy Live didn't just win. He brought the mop kissy emoji. I guess what they're saying is that your live stream went live 30 minutes ago. Did it end early or something like that?
Yeah, remember when I lagged out?
Oh yeah.
Like I didn't just reset it because I was like, "Fuck it."
I'll go ahead and I'll go ahead and vouch for Alan on that one. CK. Alan's entire internet connection went to absolute shit, and that's probably the reason why things went the way they did. All right, I don't think Alan was trying to hide anything with that glitch. It was just an internet issue. So
yeah, if it's cool, can I re-upload this on my channel as well?
You do have my permission, yes.
Thank you, sir.
So that's perfectly fine with me. And unlike some people that Louis Rossman is going after, I'm not going to sue you about it. By the way, check out Louis Rossman's most recent video. Worth a watch. Anyway, moving on. Jack Fetter for $9.99. Months ago, MC Toon pointed out the error rate increasing wildly with distance, and the presented data was essentially cherry-picked. The answer was, I need to look at the data. Nothing has changed. So, Alan, I believe that's towards you.
Oh, absolutely. A ton has changed. So if you can bring up my screen real quick.
Yes. Hang on 1 second.
Yeah. So
all right,
as I said earlier, we're sharing the same celestial sphere model, the same assumptive linear rates and whatnot. So if those rates don't correspond to reality, it's going to create a systemic error offset. And through the geometric analysis, after learning about central angle theorem, inscribed angle theorem, and tangent chord theorem, what we found is like this exact relationship has to do with the lingering effect over the arc length. So earlier when I pointed out the differences on North Peak, for example, we have these pretty big errors, right? But they're split over the timing difference that the star lingered to. Essentially what that equates to is more time, so more distance traversed. So the star has a different arc length compared to the one that we're using. So that's what creates the difference calculated when you reference the true position at the peak versus the true position at the observer position. But what you'll notice is that if you subtract these two from one another, or I'm sorry, if you add them together, they equal the drop over distance, like it's shared between us, but the offset is split over the exaggerated arc length rather than the arc length that we're doing the analysis over. So that's why we get like larger numbers in the offset. But that is it's fine. I mean, that's showing up. It's part of a geometric theorem from Euclid from however long ago that dude wrote those. And it's showing up in the measurements. It's pretty cool. So like the example that I went over with S.E. Varley, it's really easy to understand what I'm talking about because the arc length here is 9 arc minutes over the distance. And because the star lingered in an additional 4 arc minutes over that arc length, the globe ended up being off by twice the amount of the original drop over distance which happened to be the amount that the star lingered over the original arc length of 9 arc minutes. So rather than lining up exactly, that's what creates the offsets and the data for the overshoots. But the occlusions are still happening when the star intersects, when its true position intersects with the mountain peak. That's why every time when we do the refraction analysis, the globe or the flat Earth ends up recovering its geometric angle when you add that correction back in. So they end up being identical.
All right, and we will move on. This one is just an insult, just going to throw that out there, but I'm going to read it anyway because it's a super chat and I have to. For $1.99, Kenny Eaton, 603. Hi, Kenny. Also known as It's Not Flat. Why is Alan still this incompetent in 2026? You don't have to respond to that if you don't want to. You can if you want. I don't care. I'll give you the opportunity.
It seems like somebody super chatted you to not talk about the geometric intersections again.
Excellent. Flatius Earth for $1.99. Astronomy Live. Why don't you just let the top lefter strawman?
Why don't I just what?
Why don't you just let the top lefter strawman? I guess they're asking why even bother, I think.
Oh, well, that's fair. For the love of the game. No, let me.
Oh, God.
No,
that's
seriously.
That's it, though, really, isn't it, though? It's the love of the game, dude. Like, you think you're right, I think I'm right. We're going to battle it out. It's the love of the game.
No, here's the brass tacks truth of it. Like, I enjoy conducting challenging observations with my scopes, especially. And this was an opportunity to do something new and challenging that I'd never done before, which is receive ADS-B data directly from airplanes instead of just going online to see what the the website, the flight trackers say. No, get the data directly down from the airplane with an antenna. Get into amateur radio with RTL SDRs, and then using that also receive the data directly from weather balloons, and so get the coordinates and the altitude of the weather balloon. Track it from 150 kilometers away. I mean, it took a massive telescope to do that over that kind of distance. And it didn't even show up in the finder camera. Like, it showed up because I was pointing right at it, right where the globe said it should be, not at all where Flat Earth said it should be. And it worked. To me, that's wonderful. That is science in action. That is predictions matching reality.
Excellent. All right, so we're going to move on. Hang on one second. Let me just get rid of that. Okay, so for $2 from Icy Spin says the following: where does the sun go at night? So, Astronomy Live, where does the sun go at night?
Well, it goes to the other side of the Earth, away from you. The Earth rotates, now it's facing the other side of the Earth.
And Alan, where does the sun go at night?
It goes to sleep.
Goes to sleep. All right. Understood. Okay, so from just $2, Astronomy Live, did Alan contradict himself on refraction?
Well, okay, so I have issues with how Alan describes refraction because he is ascribing motives to it and talking about historically how it was determined using circumpolar stars, ignoring my method of doing it using ray tracing and weather balloons. I just fundamentally have a problem with that.
Understood.
Well, we're using,
go ahead, Alan.
Real quick, if I may. We're using vastly different elevation angles. The refraction formulas for elevations below 15 degrees are the ones that specifically are based off of the curve fitting, essentially. So just wanted to.
And again, I'm not using any of that.
And again, you're doing a different method, doing a different comparison, trying to achieve the same goal, not doing the celestial theodolite. When we do the celestial theodolite, this is what we're dealing with.
Again, this is all celestial theodolite right here. That's what this is. I'm doing the globe prediction based on the actual globe, and actually based on the atmosphere, not based on some polynomial from 100 years ago. I'm doing it based on weather balloon data from the night of the observation to do ray tracing and determine what the actual apparent angle of the plane should be and of the star.
Fantastic. I can't wait to go over it.
Excellent. All right. Deplorable ilk for £2. There wasn't any message attached to the super chat, so I'm just going to say thanks. So then we have Brett Immus _118 for $5. Astronomy Live. How did you determine that your eclipse path 1,000 years from now was an accurate prediction? ?
Well, ultimately, I won't be around in 1,000 years, right? But maybe YouTube will. We'll see. But it matches if you go to other less well-known sites that have Besselian elements for that observation. I discovered that after the fact, but yeah, it matches. And the method I use, which I featured in that video, is based on the orbital elements of Earth and the Moon, and I determined that independently. Not based on the 5 millennium canon of eclipses, not based on anyone else's website, just based on the orbit of the Earth and Moon. So go check out that video. It's on Red's Rhetoric's channel here. I brought it up only because Alan brought up Besselian elements and eclipses, and I just thought that was kind of ironic since I've got a whole video about that on this channel.
Understood. Real Cygnus for $5 says, the Laddie, Longy, and Grady were all in the Prezi, but what about the Kinney Matties Broad Dog? Jesus fucking Christ, Real Cygnus. You're gonna fucking kill me with this shit. Oh god.
The kinematics and the dynamics.
Yeah, you know what? I'm just gonna copy and paste it. If you want to reply to this, by all means, be my fucking guest. Reading that, I practically thought I was having a stroke.
No worries. My man said the Laddie and the Lonnie and the Grady are all in the Prezi, but what about the kinematics and the dynamics, bro dog?
Oh boy, it's just too much. It's just too much. Earthly Skeptic for $2. Alan, what journal are you sending the Celestial Theodolite paper to?
All of them.
Excellent. Let's see. Flatus Earth for $4.99. Clarification. Not how the radius was reached. How does the dome height of 6,371 kilometers prevent low Earth orbit? NASA lying ? Satellites ? I guess what's being said here is that if there is a dome and it's that high, how do we have satellites that are like farther away, I guess?
Yeah, so it's not physical, it's a conceptual model calculation. That's not the actual altitude of the star like in three-dimensional space. It's just used for the purposes of describing the, for linearizing the 60 nautical miles per degree rate. So.
All right, and Earth is Life for $5. Thank you very much. Alan, what is the physical location of the star if it's not actually below your feet 6 hours after it's been occluded?
Just further away from you.
All right, understood. Beasticles, again, for $4.99. Please show one example in Alan's spreadsheet and show how the globe is strawmanned and explain why the refraction amount is that amount. So what I'm going to do is I'm going to copy and paste that entire question internally so you can read it yourself.
So once again, the refraction amount is based, in my case, on actual weather balloon data, ray tracing through that atmosphere based on what was empirically measured the night of the observation, both as I made it and I also looked up the historical weather balloon data for the observations that Alan made and Heffron and whoever else from the data I had available that was made available to me. That data is all available on the GitHub, including the spreadsheets of the weather balloon data. So that is how I am calculating for refraction. Now, Alan keeps talking about geometric intersections, and he's talking about refraction recovering the flat Earth angle. But he's not talking about, he's strawmanning the globe, acting like the geometric intersection is what matters, and it's not. It's about the apparent angle of the target matching the apparent angle of the star. And when you get into targets, in this case airplanes, that are very high and very far, farther than the mountains in many of these cases, higher than the mountains in any of these cases, you end up seeing that the celestial theodolite breaks down. It doesn't match the globe. And so he's dishonest when he says that we recover the flat Earth angle. The flat Earth angle is wrong. It doesn't match what we see in reality.
All right. And let's see. Alan, do you have a response to that? I don't want to just skip ahead.
Yeah, if you can go to my spreadsheet real quick, if you can bring this up.
Yep, hang on 1 second. All right, it's up.
So to make the optical angle work for the globe when the star relative to the observer is at 206, how much refraction is needed to lift it up to the angle of 217, which is what the globe geometrically predicts as the angle to the peak from the observer?
Astronomy Live, any response?
Is that a question for me? Well, the
Yes.
difference is about 11 arc minutes.
Correct. Now, Stellarium and Settleman and Gigi Bennett, who are the premier refraction formula specialists for at angles, sub 10 degrees, give values of refraction of 13 arc minutes, 12 arc minutes, and 55 arc seconds, which we can basically call 13 at that point. And then Stellarium reports 13 arc minutes for refraction. What was the value that you got with weather balloon data?
So the value I got with weather balloon data, this was for the first Pikes Peak observation at 1 month. Well, let's see. In terms of universal time, I don't know if you have it in GMT time. 1 hour, 43 minutes, 7 seconds.
No. What was the star name?
Well, in my case, it's all related to the Hipparchus catalog. So it's HIP 109624.
Oh shoot! Yeah, I've got 39 Aquarii. I like the actual names labeled, so I'm not sure. What's the date for it though? We could do date and time.
Well, the date again is in universal time, and it's shortly after midnight universal time. Its date is January 28th, 1 hour 43 minutes 7 seconds.
28th. I think I only have 27, 31. I don't have that one specifically, but what value did you get?
So the star refraction I get is 0.222143 degrees. The target refraction I get to the mountain peak is 0.028811.
What was the astronomical refraction in arc minutes, if you don't mind? Or you just tell me again and I'll
I don't have it in arc minutes. I have it in degrees. I'd have to do the conversion.
Right. I got you. What was the DDs real quick? I'll convert it.
Here, I'll post it in the chat. And keep in mind that I am calculating for precession, nutation, aberration, all that good stuff myself. I'm not relying on Stellarium. I'm getting the values directly from the Hipparchus catalog.
Let's see. So yeah, you came up with 13 arc minutes of refraction as well. So literally the same amount. So if you add 13 arc minutes of refraction at the time that the occlusion occurred, you would be 2 arc minutes and 53 arc seconds above the peak for the apparent position with respect to the geometric.
Then why is it that with my calculation, my error is less than 1 arc minute?
Couldn't tell you. Are you using the refracted position of the peak? Because if you do that, then you'll get a 7 arc second difference between the two. If you use the...
Of course, I'm using the refractive altitude of the peak.
Okay, well, a refracted image is not where light rays converge. It's not where the physical object is, so it doesn't actually cause an occlusion.
Wrong, and I showed that with the with the water tank.
So 1 second, I disregard that premise. And then number 2, we can go to different mountain peaks where that's not consistent. So for this one, if you add an additional correction, you can get it to optically match. That's 3 corrections for that. Now, if you go to other mountain peaks, that relationship doesn't hold anymore. Like for example, for North Peak, right? You predict that you would still be geometrically above the peak by 2 arc minutes.
So I don't know why you've changed peaks suddenly, but again,
because the method of which you're trying to analyze from isn't consistent across the whole data set.
No, my method is completely consistent across the data set. Yes, you'll find some where the celestial theodolite angle wins. Although even at North Peak, looks like the globe still wins there, but those observations were more off than Pikes Peak for both models. But the Pikes Peak observation you were just talking about, I get an error of the globe less than 1 arc minute. Okay, for that 39 Aquarii, I get a globe error. Again, if I convert degrees to arc minutes, I get less than 1 arc minute error.
Yeah, that's adding 2 additional corrections to make the timing differences match what the flat Earth predicts geometrically. So
Again, Jesus
well, hold on a second, Doug. You went through this whole spiel about how we're not accounting for refraction, but you got a different value because you're using balloons. You ended up with the same values that I did, and when you add refraction into it, that's an additional correction. So you have 1 correction for globe drop that deviates from the plane. You have 1 correction for astronomical refraction to add it in. You have another correction for terrestrial refraction. All that's doing is just making it geometrically flat.
No, what that's doing is making it correct. I mean, that's the actual globe prediction. You want to straw man the globe, you can go ahead and start omitting what you call corrections, but are just part of the math of calculating what the globe predicts. If you want to straw man the globe and keep doing that, go ahead.
It's not a straw man of the globe. I acknowledge the correction, but I'm telling you that in applying it, it flattens out the arc length. The drop over distance exactly gets canceled out. There's 13 arc minutes of drop. You calculated 13 arc minutes of refraction. That should be there.
All right, I'm going to butt in right here so that we can proceed. From Jesse for $5 says, if Alan accepts that refraction would delay the occlusion, then he admits to strawmanning the globe. Did he understand delay of the stars in fish tank? ? Alan,
Perfectly. And that's why you have to take the amount that was measured and then just say it was 11 instead of 13.
Astronomy Live?
You scoff, but you want the 217.
Well, I'm telling you what I'm actually getting for the error, okay? Based on calculating it myself from the Hipparcos catalog, you end up with a globe prediction that is less than 1 arc minute. And in fact, in terms of timing error on that first Pikes Peak observation, we're at 2.5 seconds on the globe. I'm getting 13.235 for celestial theodolite.
Okay, like I said, that's not consistent across all measurements. And for example here, Lucky Peak doesn't share that relationship. The globe predicts 610 for the time of emergence, 611 for flat Earth. And what happens is the apparent position for the star at 6:7 would be below the peak by almost 3 arc minutes. So it should take 17 or 16 more seconds for that star to emerge over this peak, but that didn't happen.
So if you want to share my screen again.
So you're saying that you're going to need more refraction to compensate to just recover the flat Earth angle.
The amount of refraction is going to depend on the conditions at the time, the altitude of the observer, the elevation over the horizon of the peak and the star, etc. You gotta calculate it correctly, okay? And when I've done that myself from the Hipparcos catalog directly, what I see is this. This is the error across the data set. And yes, for the Pikes Peak observation, I get a lower error for the globe than for the celestial theodolite. Across the data set, the error for the globe has a root mean square that is significantly lower than flat Earth. And I do mean statistically significantly at a p-value of less than 0.001. The celestial theodolite root mean square error is 6 times that of the globe.
To optically recover that and get that baseline, you have to agree with our angle geometrically. That's a fact.
Does that look like an agreement to you?
Looks like you did a completely different thing and compared the globe to itself instead of comparing geometric intersections or even the refracted position with respect to the GFG. Yeah.
All right. I'm gonna give Alan the last word here before we read the last super chat.
Okay.
Yeah. So 13 is not the same number as 11. It doesn't take a super genius to see the difference between that. You're exactly compensating for the amount needed, which entirely recovers the flat Earth angle every single time. That's what every one of those graphs I show shows.
And for £5, this isn't the last question, just the last super chat.
Yeah, can we burn through? Can we burn through these kind of quick? I got a dip.
Yeah, absolutely. I'll be very, very quick. Deplorable Ilk says, Alan denies using optical measurements. So how did he see the occlusion? Question mark. Answer that, and it's 2 more.
We're comparing timing intervals to what the optical measurement would predict. And we can do a geometric analysis based on true positions at that time of occlusion to differentiate between optics and Euclidean geometry.
All right. And this is a question from 82 Productions. It says, given that it's a gorgeous cloudless, albeit cold, clear night tonight, why are we wasting our collective time with idiots who refuse to accept reality when it stares them in the face? I will answer that because it's fucking cold outside and I don't feel like freezing my ass off. So there's that answer. The second one, which I believe is more relevant to this, Alan, do you agree that weather balloons transmit back accurate data?
Sure.
All right.
I don't see any reason to doubt it off the cuff.
All right. And Astronomy Live, do you agree that weather balloons transmit back accurate data?
Yes, I do.
Excellent. Okay, cool. So with that, Astronomy Live, I'm going to give you a moment to say your last word. And then, Alan, I promise you that you would get the last word overall. This is me meeting that promise. So Astronomy Live, last word, closer, say what you got to say.
Yeah, so I feel like nothing's really going to change here with Alan's take on things, and I wasn't expecting that, but I hope I've demonstrated to people sitting on the fence that the flat Earth and the celestial theodolite do not match reality as well as the globe by a country mile. I've done these observations myself now and recapitulated the radius of the Earth, and when I look at the flat Earth versus the globe error, I see that the globe consistently fits better than the flat Earth. And when I look at Alan's data set, I see the same thing across the data set to statistical significance that is extremely, extremely high, and with an RMS that is 6 times higher for flat Earth. All of this tells me that the Earth's not flat. Big surprise, right? Well, again, this is based on his method of doing things with the airplanes. And then I went and verified this by picking a target even higher, even further away, a balloon, a weather balloon, and directly measuring the angle to that weather balloon. And what do I see? I see that it, again, matches the globe, and it does not match the flat Earth at all. If flat Earth were true, I wouldn't have even been able to find the balloon. It would have been several times the vertical width of the field of view outside of the field of view. You want to talk about being outside the field of view? It would have been outside the field of view if Earth were flat, and I would have never found it because it was far too dim to see with any kind of finder camera or even the refractor riding piggyback. The only thing I could see it with barely was the main telescope, which has an incredibly narrow field of view. We're talking 20 by about 11 arc minutes here. So the vertical field of view of that widescreen video is only about 11 arc minutes. Okay, that is basically tiny. It's like looking through a straw. Okay, the moon and the sun in the sky are about half a degree, right, or about 30 arc minutes. So imagine 1/3 of that. That is the breadth of the field of view of my telescope in that situation, and you're dealing with something that is incredibly far away, incredibly hard to see. If it's not in the field of view, it's like finding a needle in a haystack. You'll never find it. And this isn't the first time I've done something like this, where I've needed reality to end up matching the globe. I've needed to account for refraction. I've needed to account for the drop of the Earth. The shirt I'm wearing is Starship Flight 4. This was the first time that I saw an intact Starship from Florida in broad daylight. And I tracked it, again, open loop tracking, meaning not based on seeing something in a finder camera, but rather based on finding it directly based on what the globe expected, based on where the globe said it would be. And doing that, I was able to correctly track it and find it popping out of the blue sky during engine shutdown. It's not even visible before then. And then when the engine shutdown happens, suddenly it's right there in frame. Did that again from the same spot we filmed that balloon from, the Sunshine Skyway Bridge in Tampa, thanks to the fact that the Earth is a globe, and reality ended up matching that. So I was able to track that open loop based on the trajectory of Starship launching from Texas minutes before I saw it flying south of Florida. If Earth were flat and it was trying to get up there somewhere, it would be at the wrong angle, just like this balloon would have been at the wrong angle if Earth were flat. Yes, I've accounted for refraction in these observations, but when you start to look at things that are 6 degrees above horizon, refraction starts to reduce. And with a balloon this far away, the delta between the flat Earth and the globe is far higher than refraction. Refraction doesn't explain it. Even if you looked at just the geometric angle and pretended refraction wasn't a thing, you would still see that the globe would win by a huge margin. So with all that said, I don't think that Alan's going to change his mind. I didn't expect that going into this, but I do hope that people around on the fence who aren't in that rabbit hole can see the reality that is at play here.
All right. And Alan, you have the final word, and we will conclude after that.
Okay. So throughout the debate, geometric analysis of stars occluded by mountain peaks was avoided, and the implication of adding the drop over distance back in as a refraction correction was ignored, and said that that's, stated that that's part of the globe. Well, if you were correcting optically for the geometric difference between flat Earth and globe, and it just so happens to be that you're correcting the baseline such that it's flat Earth every time, then that's not, you're not proving anything. We can make the prediction based off of just using rise over run to the peak, and when we add the arc length back, we should be off by the elevation difference that we failed to account for. I showed that several times in the spreadsheet. That's never the case. I also showed the how the intersection differences because of the stars lingering affects the air in the measurement, and how that relates to the central angle as per Euclid's theorems on tangent and chord theorem, central angle theorem, and inscribed angle theorem. To do the complete geometric analysis of that, you have to understand those theorems. They're pretty straightforward though. And then when you get into comparing, what the globe geometrically predicts for its baseline to have the deviation for refraction to explain the deviation from that, you'll see that the Earth curvature, when we do a Gaussian distribution on the occlusion angle versus the predicted angle for rise over run versus the observer-centric position of the star, with the rise minus globe drop over run, we see that the globe is outside of the Gaussian distribution pretty much every single time, and flat Earth is within spec. Like using just trying to compare the globe to itself with optical angles isn't going to yield a different result. A large portion of the analysis offered tonight was circular, and I look forward to going through the new data and getting back to him on this. So I'll see you guys on the return. If anyone has any questions about the celestial theodolite, the method, or wants to contribute to data, etc., or participate, all the information can be found in the Discord, and the link that Red's put for the presentation, where all the resources are here and available as well.
Yep. And to both of you, before we end, I need both of you to send me all the relevant links so I could put it in the description so that everyone can find it. So ladies and gentlemen, if you would like to find any of these details, again, it's in the description down below. I would like to thank both of you for not turning this into a cataclysmic shit show. That is very, very nice. And I would very much like to set this up again a month from now, or a month and a half from now, however long it takes to go over what Astronomy Live presented, so we can do this again. In the meantime, guys, thank you very much for watching. This has been great and fun. And with that, we are out. Peace out. Bye-bye.
All right. Before I dip, can you